Good afternoon, everyone. So you had a good time with Raksha Bandhan. So now, so is there? एक या दो कितना है? एक ही है. Okay. Anyway, we'll start with the topics there. And before I start, let me just give the topics of today's class. See, today we'll deal with two areas, all the basic concepts. The first one will be in terms of, last time when we started with the development part, I have discussed about DAE, Atomic Energy Program of India. Today we'll learn about here concepts related to nuclear technologies. After going through about orbits, type of launch vehicles, those concepts, now today I will be focusing on the nuclear technologies. And one very important one will be research reactors. Research reactors. Then we'll discuss about power reactors, which are used for power generation. We'll look into different types of power reactors. And then we'll learn about how the controlled chain reaction, fusion reaction is being carried out in such reactors there. Then we'll go into another very important topic. Many times when you read, you'll come across this term called nuclear fuel cycle. Right, so what do you mean by the term nuclear fuel cycle? Right, all those things, though I have, in the beginning with part of development, I have said that today India is a nuclear capable country. We are using nuclear technology for both civilian peaceful use, at the same time for military purposes. So we need to understand this term called nuclear fuel cycle. So that is again a basic concept, fundamental concept to be understood. Then we'll, as I've given you the application of nuclear technology into agriculture, medical science, industries, we will review through the report. I'll be covering through Department of Atomic Energy report. This soft copy will be uploaded to the student portal, where you will have all the details of that. Okay, how BARC has developed respective technologies into various such areas. We'll go into that part. Second part of the discussion will be, again, we'll go into different area, concepts part, that is in terms of defense technologies, right? So since we have already learned about areas from DRDO, what DRDO as a part of lab establishment has developed in the last 55 years. After its establishment in 1958, in the last, you can say 58 years, where DRDO has gone into that. So there I have mentioned about missiles, fighter crafts, helicopters, all those things. But today, we'll look into the concepts here. Now concepts here, like for example, when we say ballistic, what do you mean by ballistic? Though you are aware of it. What do you mean by cruise word? Then when you talk about military craft, so there in terms of military crafts, there comes first generation, second generation, third generation, fourth generation, what type of military crafts we have in India. Then in terms of, as I said, different type of warships are there. Today we'll look into their features. There I have just mentioned, but today we'll look into details of that, right? Now in terms of missile technologies, I have not given you too many information into that. I have just mentioned IGMP, Integrated Guided Missile Program. But today you will be going through each and every missile with their range, how much is the range of that missile, what is the so special feature about that missile, particular missile, plus how much warhead the missile can carry. At the same time, besides all this one, we will also learn about, we'll go into, as I said, I'll be covering from reports. We'll go into the few of the important reports. Right, we'll look into what is given in the India Yearbook. Right, what is given in the such kind of Yojana December month magazine, what information you'll find there. So that when you supplement your concept with those areas along with facts, you are in a position to attempt maximum question in the prelims exam or write 200 words in mains exam. So look into that kind of thing. The two areas will be covered. Next class, when we'll meet there, I'll go into the area of energy resources. Though today we'll be having this reactors, technologies and all, but we'll go further into that, right? Now let's look into first part of that, nuclear technologies, research reactors. I have already mentioned in the classroom that research reactors are used for training, education, right, in terms of generation of radioisotopes or any kind of a test bed, new type of technologies, right? In terms of India's development, if you look at here, let me first open that soft copy here. Now look at here, research reactors, research technologies, reactors technologies there. You'll come across various development, and it has happened with due course of time. As the technology advances, right, there is more and more development there. But most of the, remember that, research reactors, let me uh, mention here, is based on, so when we talk about nuclear reactions, right, so nuclear reactions, so one part comes, mostly it comes into what? Fission. One can carry out fission. Now what is fission here? Where the radionuclei splits into daughter nuclei, right? That is what fission word comes there. And sometimes the nuclear reaction could also be fusion, where light nuclei can combine together to form heavier nuclei. And you all know that the source of energy in stars or suns is the nuclear fusion reaction, where hydrogen combines together and then form the helium. Now fusion reactions are also sometimes called as thermonuclear reaction, because combining light radioisotope, light nuclei requires very high temperature of the order of 150 degrees centigrade. That is the order of the time, or 1.5 million degrees Celsius is required. Thermonuclear reaction. This is also called as that. It is not possible to carry out in room temperature. You cannot have nuclear fusion reaction. We require very, very high temperature. Then only light nuclei like hydrogen can come closer, can react together, and can give rise to new type of element like helium and all this. They require very high temperature. That's why the fusion reactions are referred to as thermonuclear reactions. But the fission reaction here, it can be brought about, right? It can be brought about simply with slow neutrons. So let us first understand this part, concept part of that. Then I'll come to the research reactors and power reactors, everything. Now let's understand here. So let's say, for example, you all are aware that uranium, right? Uranium as a element exists in two isotopes. Now comes the question, what do you mean by the term isotope? Or sometimes you come across the word radioisotope. Radio word is linked with radiation, which give rise to alpha rays, gamma rays, beta rays, those kind of things. See, isotopes are those elements, those things where same atomic number but different mass number. So when I'm writing here uranium-232, so here atomic number is 92. That is equal to number of electrons, which is also equal to number of protons in a neutral atom. When you take an atom of an element, so the number of electrons has to match with number of protons so that it becomes electrically neutral. Right? So atomic number refers to number of electrons. Now from chemistry, electrons are involved with reactions. All the chemical reactions are based on the electrons part. So the electrons comes in. But where do you find protons? Protons are those atomic particles which are found in nucleus of an atom. Right? That's the word the nuclei comes. So when you say 92, so here means 92, there's a number of electrons which is also equal to number of protons. The basic concept part of it, that's what I'm writing on the board here. Now when you say 235 is a mass number. Now mass number here is of uranium, what I've written is 235. Now what do you mean by mass number? That is the total weight of a nucleus of an atom. Total mass of a nucleus of an atom. And that is equal to protons plus neutrons. So sometimes when you read there, it will be given here is which is referred to number of nucleons. There is a word called nucleons, which is nothing but protons plus neutrons. Together they form the nucleons. Right? So when I say 235, that means total number of protons plus total number of neutrons found in the nucleus of a uranium-235, this nuclei there. So number of protons is equal to number of electrons. So 92 is the atomic number. So if you subtract 92 from 235, whatever number we'll get, that will be number of neutrons. Now what happens there? As nucleus of an atom, the central part of an atom becomes heavier, right? So it becomes unstable. So there's something called N by P ratio, neutron by proton ratio, right? Number of neutrons and protons. It has to be there, that is what comes here 1 to 1.5 for remaining stable. When that ratio exceeds, the nuclei become unstable. And then in order to gain stability, it disintegrates. What is called radioactivity. It disintegrates, breaks. And that disintegration is carried out in terms of radiations or particles. right? Now, uranium-235, this nucleus, when it is struck by slow neutron. Now, here is what? Slow neutron. Right? Sometimes you'll come across the word thermonucleum, thermoneutron. Thermal means, here means high energy. So when it is slow neutron, it is captured. It is captured by the uranium-235. It converts into uranium-236, which is unstable. It becomes unstable. It's not stable there. It becomes unstable. And then it disintegrates, divides, breaks into nuclei. So it disintegrates. So it disintegrates into barium, then krypton, and then it gives rise to three furthermore neutrons. This is basic science which I'm talking about. When you read about in the general science book about nuclear reaction, fission reaction, it is what is mentioned. It breaks into barium, krypton, and neutrons. Now these neutrons are fast because they are emitted with more energy. They have high energy. When I say fast means they contain high energy. But in order to bring about next reaction, it has to be slowed down. It has to become slower, right? So that's what I've written here, slow neutron can bring about this disintegration or called fission, right? Fission or breaking into that. But what the neutron is produced in the reaction are faster neutron, has to be slowed down. There's one reaction. But there is another type of uranium, I have used the word here, isotope. Now what is isotope? Same atomic number, but different mass number, right? So here, there's another one which is called 238. Now 238 does not undergo fission. If you strike with a slow neutron, it will not be there because what I've said here, N by P ratio. N by P ratio has to come into that particular range. Then only it becomes more that, then instability happens there. So when you talk about this one, so this is not broken down with slow neutron. It does not undergo any kind of a disintegration. So that's why this concept you have to remember that all reactors, whether research reactors or power generation reactors, worldwide, the main fuel is uranium-235. Right? Which is because uranium-235 can only undergo disintegration or fission and breaks into daughter nuclei and generate further more neutrons which can bring about other reactions. Right? Now, when we are using under lab condition, right, we need to control the reaction. The reaction has to be within controlled condition. If you are not under controlled condition, the reaction will keep on happening continuously. It will generate huge amount of energy. Yield will be very high. So for practical purpose, for power generation and the research purpose, we need to control the reaction. And how we can control the reaction? We can control the reaction through the number of neutrons. If there's more neutrons, more reaction. If less neutrons, less reaction. So let us bring about further more concept. I've just mentioned here, let me bring about further more concepts. When you talk about reactor technology, there are certain components of any reactor, right, which you are again aware. Moderator, coolant, right, then comes here, controller. So there are few things here. So let me first, just here, I'll not remove the reaction here. Just simply mention here that when you talk about here reactions, so components, I'm just simply writing here, components of a reactor, and it is I'm writing here general aspect. You take any reactor worldwide, whatever the earlier type of reactors or advanced reactors, these are the few components which you have to always keep. The first thing comes here, fuel. What type of fuel it burns. Whether it uses uranium, or it uses thorium, or it uses plutonium. The first component always comes fuel. On what fuel the reaction works. Second component, I'll give the detail also there. Here the word comes moderator. Right? Now, I'll write on the board only, what do you mean by moderator? Moderation. हाँ. हाँ, तो बढ़ जाएगा तो नहीं, फिर भी क्या होता है? हाँ, तो मैं बता रहा हूँ कि अगर इसके बीच में है, तभी होता है. Now, what he is asking that, कि जब यहाँ पर तो क्यों नहीं डिसइंटीग्रेशन होता है? यहाँ भी तो रेशियो अधिक आ रहा है. Is it 238 and 92? It should also undergoes fission. So there's something here, the concept is in terms of odd number and even number. Okay, how many number of protons, neutrons are there? General aspect comes what? It has to between N by P ratio has to be 1 to 1.5 to remain stable. If it exists more than 1.5, it becomes unstable. Certain case यहाँ भी हो सकता है, ऐसा नहीं है, it can also disintegrate. But it generally what happens that it capture, जो न्यूट्रॉन जो कैप्चर होता है, that is very very slow, बहुत slow होता है वहाँ पर, क्योंकि बहुत सारी forces है, it is not that only one force, lot of forces happens there. जैसे जनरली क्या होता है, ये याद रखना है कि 235 क्या होता है, उसमें ऐसा रेशियो होता है कि इट इज एबल टू एक्वायर वन मोर न्यूट्रॉन. जैसे फॉर एग्जांपल अगर आप यहाँ सब्ट्रैक्ट कर दो आप 235 माइनस 92, तो यहाँ आपको ऑड नंबर मिलेगा, है ना, ऑड नंबर ऑफ न्यूट्रॉन्स आएगा, राइट, वन एंड व्हेन यू प्लस वन तो इवन होता है, तो वहाँ डिसइंटीग्रेट करता है वो. इस जगह पे इफ यू सब्ट्रैक्ट 238 माइनस 92 यू गेट इवन नंबर्स, तो जल्दी वो कैप्चर नहीं करता है वो, राइट, बिकॉज अगर जब डिसइंटीग्रेशन होता है इवन नंबर, तो वो कुछ है यहाँ फैक्टर, बट जनरल एस्पेक्ट ये चीज़ होता है कि ये रेशियो इसके बीच में रहा तो स्टेबल होता है. अगर 1 से कम हुआ अनस्टेबल होता है, 1.5 से ज़्यादा होता है तो फिर अनस्टेबल आता है, उससे यहाँ पर होता है. लेकिन यहाँ पे पॉइंट ये ध्यान रखना है कि यूरेनियम ऐसा नहीं है कि 235 ही केवल है, 238 भी है. नाउ यूल अंडरस्टैंड कि जैसे व्हेन आई कम टू ईच एंड एवरी रिएक्टर टेक्नोलॉजी यूल गेट टू अंडरस्टैंड. सो व्हाट आई वांट टू से, फ्यूल कैन बी 235, दिस व्हाट आई mentioned here. It can be plutonium, it can be thorium, it can be any type of radioactive nuclei which undergoes fission. That's part. What is second component of any research reactor is, or any power generation reactor is a moderator. What is the role of moderator? It has to slow down the fast neutron. So very simple sentence I can say here, and I'll give example also. The role of is it slows down fast neutrons. हाँ. अच्छा ठीक है, फ्यूल का ये कि विच अंडरगोज फ्यूजन, जैसे यूरेनियम हो सकता है, लाइक फॉर एग्जांपल यूरेनियम कैन बी देयर, और समटाइम्स डिपेंडिंग ऑन द टाइप ऑफ रिएक्टर इट कैन बी प्लूटोनियम, और वन कैन मेक अ थोरियम बेस्ड रिएक्टर. दैट डिपेंड्स ऑन कि व्हाट टाइप ऑफ फ्यूल वी वांट टू यूज इन द रिएक्शन पार्ट, राइट. नाउ हियर व्हाट इज द रोल ऑफ मॉडरेटर? इट स्लोज डाउन, because for uranium 235 to undergo fission, it requires slow neutrons, not the fast neutrons. That's why I have not removed this part, because when the neutrons are emitted, they are the faster neutrons. Now here, this part can be done by using materials like what is called heavy water. I have used the last time the word heavy water. Heavy water is deuterium oxide, it's called D2O. Right? Hydrogen, just like uranium exists in 235, 238, hydrogen also exists in 3 isotopes. Right, 3 isotopes are. No, I'm saying that, see here, what happened? 235 captures neutrons, it becomes 236. 236, it happens within the process there. So what happens there? It becomes here the ratio it becomes such a way that it breaks down because of the capture there. But no, it will not be stable, it will become unstable. When it acquires neutron, it becomes such a way unstable. Because of this even number, which I said, this becomes even number. Yeah, threshold capacity also there. That's what I say, there are number of factors are there. So natural uranium 235, that undergoes the process. But when you say 238, this 238 when I said, so here it will not acquire that kind of a limit there, where it will become unstable there and breaks into that. Because if it captures the neutron, so what will become in the process here? 239, right? This is what will become. That I'm drawing this as a part of the within the process it generates there. So there are number of factors works. But what you have to keep for the UPSC exam or any exam is that 235, which after acquiring the neutron, it captures the neutrons and then becomes unstable and breaks down. Now again the question is that, is it only barium krypton? No. It can be any other type of element. For example, I have mentioned barium krypton. It can become strontium also there. That only the thing is that it tries to maintain what is called the numbers there. So actually, again remember that. One more concept which comes here, this energy, I'll be coming to energy part also. The energy is because of Albert Einstein's theory. There's something called as here, which you also know that. Change in energy happens with the mass number. Whatever the mass happens there, that gets converted into energy, and that energy, and that energy, atom bomb, uncontrolled reaction. that energy comes into that part, right? So just simply remember that here, all worldwide research reactors uses the uranium there. There is 235 also, 238 also. It's always a mixture. But it's 235 which is able to capture neutron and breaks down into daughter nuclei and generates more neutron here. But these neutrons are faster. And in order to be captured by another uranium-235, it has to be slowed down. There comes the role of moderator. So what is done in the research reactor or any kind of power reactor, heavy water is one component which can be used as, because heavy water is slightly heavier than the normal light water, what you call H2O. Right? Hydrogen exists in 3 isotopes. There is called protium, that is the hydrogen, then deuterium, and tritium. Third comes here. So this is slightly heavier, which is able to slow down. See, remember that. When to slow down is not that it's a very large slow down. It's very, very, energy is in the form of electron volt. Electron volt is very, very less. As compared to normal energy, what we're talking about, very, very less energy we are talking about here. Now what happens is, we can use moderator like heavy water, but sometimes with the reactor technology, it is possible to use light water also. Normal water can also slow down. But what we have to use? Pressure. Pressurized. Right? When we do pressurized, or we can say density of water. See what I've said here, heavy water is slightly heavier. If density becomes more, so it will be able to slow down the neutron. What is slow down neutron? You have water. When neutron pass through water, slowly what happens? It loses the energy. It loses the energy in the process. That's what happens in this case. But for explanation purpose, I have mentioned here heavy water, right? I have also said what? If we do not control this neutron generation in a research reactor, it will keep on happening, keep on going there. And becomes a very, very uncontrolled, because amount of energy generated will be again added up continuously, become huge. So we need to again look into the neutrons there. And for that purpose, there is a third important component, what is called controller. And we'll see today's class the reactor design also there. See, when we say controller, controllers are always in the form of rods. You'll find controller rods are there, right, which is lowered or taken out inside the reactor core of the reactor. Now controller, what is the role of this one? It absorbs. The role is here, is absorbs, right, it absorbs neutrons. So we are able to maintain the number of neutrons within the reaction vessel. Because if we go for a large number of neutrons, reaction will be more. Reaction will be more, then it will generate more energy. So the role of controller in the form of control rod is to absorb. It absorbs neutrons, excess neutrons are absorbed with that. Now in this case, the preferred material which is used worldwide, long way back, graphite used to be used, graphite. Right? But then today, graphite has been removed because of the reason that Chernobyl disaster, right? Ukraine, 1996, Chernobyl reactor, there's an accident which happened, was because of high energy, high heat energy, and graphite rods were used that time. That caught fire. You know that graphite is a form of carbon, right? That was the problem which happened in way back 30 years back in Ukraine, Chernobyl disaster there. Worldwide, including India, today we use one preferred is boron. You'll find boron elements is used. And I'm providing this all kind of factual information so that any exam, they ask you, at least you know that. Then you'll find cadmium. Cadmium borons are able to absorb neutrons. They are able to absorb completely neutrons, so that the available neutrons will be less. Reaction will remain within controlled condition, right? There's again one more component. What is more one component? Any nuclear reaction which is happening, it will generate heat energy. High heat energy will be there. And we need to maintain the temperature also there. So there's something called coolant, right, which is having dual role. I'll come to that. See here. The fourth part which comes coolant. Now what is the role of coolant? To keep the temperature. So let me write here. I'll write on the top here. To keep a temperature of the core of the reactor, where the reaction is taking place. Core of the reactor constant. Should not go to very high heat energy. And second role of coolant is that extract excess heat energy. Right? Whatever heat is generated, to take that heat, excess heat, and transfer into the medium where water can become steam, and steam can run the turbine generator for power generation. So another role is that, plus there's another role is that to exchange heat. It has to exchange the heat there. let me to exchange heat there. Right? Now controller here, absorb neutrons, at the same time also controls amount of heat generation. You can also write here, plus control amount of heat generation. Amount of heat generation. Let me just close this one. So band kar dena. It also controls the amount of heat generation. Ki how much heat is generated. That can also be done. So let me, I've just made so that I can draw a rough diagram here. You'll find that you have this kind of core. And again remember that this all is what? Shielded. The heavy walls are there. So reactions, radiation should not go to the environment. Right? It's built in that. Within that you will find here, what is called here, the fuel is kept. There's something called fuel bundles are there. You'll find the bundles will be there. Whatever, uranium, thorium, whatever, but worldwide, uranium is the preferred material. And controller rods are like this. You'll find controller rods, they're like this one. These are controller rods. Right? Now, in order to exchange heat or keep it there, we require what? Coolant material. So coolant has to go through a pipe. So I'm drawing a kind of a reactor design. See here, what I'm designing here, I'm just drawing this part, just to make you aware of this type of reactors what we are using. Now here, we circulate what? Coolant. You'll find the coolant which goes there. Right? Coolant which will flow through the core. So that whatever heat is there can be taken out to the outside the core of the reactor. Okay? Now this heat has to be exchanged. It has to be exchanged to another medium there. There has to be another medium where the heat has to be. See here what will happen? Because of nuclear reaction, heat will keep on generating. That heat will be taken outside. Let's say here the water flows. This water goes there. Just a rough diagram to make you understand here. So it goes here. But here what will happen? Here water will be hot. This is hot water. Will be high temperature. Right, here we are circulating cold water and this goes to hot water. Now this coolant, now I'm writing here, the coolant if you look at, coolant can be normal water. We can cool using the light water. When I'm using the word light water, it's normal water. Right? Cold water can be taken from river or sea and ocean. That can also cool there. Or sometimes we can also use heavy water. Heavy water also as a coolant. Few type of research reactors, they employ another type of coolant, what is called liquid sodium. Right? I'll be coming to what type of reactor require liquid sodium also. Like liquid sodium is also able to absorb heat. Right? Three type of I have written here: normal water, or heavy water, or liquid sodium, which can go to the core of the reactor and take the heat there, so that this temperature within the core remains at a constant level. Right? Now what happens here? This is what is said exchange. Here is what's called exchanger. This is a heat exchanger. And what happens in heat exchanger? It will generate what? Steam. Because you require working medium, no? which will generate power, electricity. And this steam is passed through what? Turbine there. This is a turbine generator, which is basically what? Mechanical to electrical, as the gas turbine, mechanical to electrical. And that produces what? Electricity. This is what the general aspect comes. Just a rough diagram, just to make you aware. Any kind of reactor design, you'll find this is how it works there. Particular power reactor works in that way. Right? I'll also explain one more aspect. What I've said here, controller rods, they absorb neutrons, excess neutrons, plus also control amount of heat generation. You'll be able to understand in a very clear way. See, let's say, if we take this rod, lowers the rod inside, right, let's say we lower it. So what will happen there? More this controller rod will be inside there. It will absorb more neutrons. So less number of neutrons will be available for reaction. So less amount of heat will be generated. Right? If you take this outside, if we take it outside, if there is less boron or cadmium within the reaction vessel. That means here where the fuel is there. So less number of neutrons will be absorbed. That means available neutrons are more. If more available neutrons are there, more reactions. More reaction, more heat generation. So today the technology has advanced to a stage where automatically it is controlled, lowering and taking up. So we can control the number of neutrons in an exact way we want to generate heat energy or carry out the for power generation. तो दो चीज़ को याद रखना है, केवल न्यूट्रॉन एब्जॉर्प्शन का नहीं है, कितना हमें हीट जनरेट करना है, ज़्यादा जनरेट करना है, कम करना है, वो भी कंट्रोलर के द्वारा हम कंट्रोल कर सकते हैं. तो उसका सिंपल सा तरीका है कि जब हम इंसर्ट करेंगे तो ज़्यादा कंट्रोल मटेरियल जो है बोरॉन या कैडमियम इनसाइड द फ्यूल कॉम्प्लेक्स होगा, तो ज़्यादा न्यूट्रॉन एब्जॉर्ब होगा. लेस न्यूट्रॉन अवेलेबल रहेगा रिएक्शन के लिए, तो लेस एनर्जी विल बी जनरेटेड, हीट एनर्जी. तो वी कैन बाय कंट्रोलिंग द अपवर्ड एंड डाउनवर्ड मूवमेंट वी कैन कंट्रोल. और जब हमें रिएक्शन को बंद करना होता है, व्हेन यू हैव टू शट डाउन द एंटायर रिएक्शन, वी विल इंसर्ट कंप्लीटली so that all neutrons are absorbed, reaction is stopped. So you can say that controller is also a safety feature. Ki anytime any error happens, any fault happens, any problem happens, so what we can do, we can put all inside so that all neutrons are absorbed. No neutron is available, reaction will stop. So that is what a controller has got the part of it. In order to generate power, we require heat exchanger and coolant material. So for that we have heavy water and all this. Now in India, I have said that we have 3-stage nuclear power generation program, and I have also given you the notes part. That first part is boiling water reactor, then pressurized water reactor, then we have developed fast breeder reactor, and then now latest one is thorium reactor or advanced heavy water reactor. Right? So let me first, what I'll do is that I'll put it here. I'll just remove this part. I'll first explain it. That I'll give you the written part also, one paragraph each. But first you understand what exactly these reactors are all about. See now, when we say boiling water reactor, see remember that it is very unfortunate that this type of reactors are still used in developed countries. But boiling water reactor is what? First generation reactor, first generation. Right, earlier, right, 40 years back, 50 years back, the first type of power reactor which was made was boiling water reactor. But Japan, right, Japan still continued to use the boiling water reactors, the older type of reactors, which basically met with an accident in Fukushima in 2011. So now, very simple concept is that. See, when we say boiling water reactor, so what happens in boiling water reactor? Let me give you all the ingredient here. So boiling water reactor uses what fuel? So here fuel is uranium. But again remember that whenever uranium is used, it is not that pure uranium-235 only will be put up there. Is always a mixture. And again, not mixture, this means not that uranium-230 by 238. It is a form of oxide or fluoride. Some form has to be there. So let me write here. It is basically uranium-235, uranium-238 oxide mixture. This is what is used as a fuel bundle. Rods are there. You'll find cylindrical rods are there, which are packaged with this kind of fuel there. Now here, what is the coolant here? Coolant is normal water. Right? Normal water, what I'm writing here, light water. Now what this boiling water reactor does? The water which is passed inside, this is the diagram, water which is passed inside, that gets converted into steam. Right? Same water is converted to steam. So there will be what? Because of inside when you pass water, so there will be steam also and water also. But for generating power you require steam. So what happens here is that, here coolant, right, light water is there. Now it is a moderated, if you look as moderator, moderator will be again here, as I said, preferred is what? Heavy water. In India, we have used this kind of thing there. And controller will be, as I said, boron or cadmium. In India, we are using boron or cadmium based. So I've simply written boron there. Now what is a boiling water reactor? It converts normal water into steam. There is water steam mixture. Steam is separated, right? And here, when the steam is separated, the steam will run the turbine, and then the water again gets circulated back. ठीक है, तो यहाँ boiling water reactor older reactor design है, जहाँ पे हम water को ही steam में convert करते हैं, और steam को separate कर लिया है. There is steam separation is there. The technology is the steam separation. That steam moves the turbine. and the water is separated. That is a earlier type of reaction. We today also have, ऐसा नहीं है कि we don't have. We do have such boiling water reactor, but very less in number. In Trombay we have, right, Rawat Bhata, but slowly it is all has gone replaced by pressurized water reactor. ठीक है? तो इसमें केवल एक ही सिस्टम होता है जहाँ से हम वाटर को कन्वर्ट करते हैं स्टीम. I'll give you a paragraph, but just only for understanding I'm writing here. Now compare, now let's say, compare with pressurized water reactor. यहाँ पर word क्या है? Pressurized, right? Now I'll write here this way. When you look at pressurized water reactor, see, I'm just simply writing here water reactor. So pressurized water reactor is a modified version of boiling water reactor, and there's a two type. Either it can be pressurized light water reactor, it could be pressurized normal water, we can use a light water reactor, or it can be a pressurized heavy water reactor. We can use heavy water for both cooling and power generation, both coolant and moderator we can use for heavy water. It can be both. ये कंसेप्ट को याद रखना है कि कई बार अगर ऐसे क्वेश्चन आता है एनी टेस्ट सीरीज प्रोग्राम और लेट्स से this is one area where UPSC has not gone till yet, right? See, nobody knows that when the question can come in what form in the exam, but at least you are aware of it. So let's say a question comes in the exam, and it uses that pressurized water reactor can be made to run with the both normal water and heavy water. It will be correct. What is very aspect here is pressure. Here the main aspect comes pressure. Like how it differs, I'll tell you that. See here in this case, again the fuel. The fuel will be again uranium-235 and 238 oxide. The fuel is the same, right? In this case, coolant, if you look at coolant, in terms of heat exchange is the normal water. That's what I say it is nothing but an advanced version of boiling water reactor. Only what is we are working with the pressure component. I'll explain how the pressure component works. But again remember that moderation, for moderator we have to again go for the heavy water. But here, no, sorry, here moderation is also done by light water. Sorry, here the normal water will be there. Heavy water is used there. I'll explain how the normal water works with moderator also. And controller will be the same thing. That's the boron or cadmium. Now understand here. Here, water is heated to superheated temperature, superheated. Let's say 250 degrees Celsius. But water will not boil into steam. So remember that. What I've said here, what happens boiling water reactor? It is boiled into steam. Now what happens pressurized light water reactor? It uses pressure mechanism, just like you have pressure cooker. As we cook the food. So what happens pressure cooker? When we give heat and it is under the pressure, so it generates what? High heated water. So what is done in pressurized light water reactor? The normal water which is passed is under extreme pressure. The temperature of the water goes up to 250 degrees Celsius, 300 degrees Celsius without boiling into steam. You can say superheated water. The water still is liquid, has not converted to gas, not into steam, but the temperature is very, very high. That is what mechanism happens. And what is the advantage? This superheated water which passes here, so this heat gets exchanged with another pipe. You'll have another pipe which has the normal water. So, अगर कोई ऐसा आप इमेजिन करो कि एक वेसल है जहाँ पर 300 डिग्री सेल्सियस का ऐसा कोई लिक्विड है और दूसरा एक वेसल है जहाँ पर नॉर्मल पानी है, वाटर है, तो उसके टच में आएगा तो क्या होगा? वो स्टीम कन्वर्ट हो जाएगा. तो स्टीम कहाँ बन रहा है? यहाँ बन रहा है. और ये वाटर क्या है? इसके अंदर फिर सर्कुलेट होता रहता है. तो इसको ये समझना, मैं लिखवा भी दूंगा. फर्स्ट अंडरस्टैंड दैट कि व्हाट इज द थिंग हियर. इन प्रेशराइज्ड लाइट वाटर रिएक्टर, one uses the light water for moderation also, slowing down also there, right? Because the water, again remember that density of water also changes with temperature, right? Like when you have more boiled water, more it will be light, will be less dense. जब cold water होता है तो dense होता है, right? अगर boiled water होता है उसकी density कम होती है. You know that अगर कोई हम गैस तो वो density जो water है वो temperature पर depend करता है. That works on temperature. So what is very important thing to keep in mind is that this is a advanced technology. This is a very advanced technology where we use the simple plain water And that can moderate the reaction, that will slow down the neutron also. At the same time, generate high heat energy, which can convert into steam and can move the turbine. On the other hand, when you look at this pressurized heavy water reactor, so here the fuel is again uranium-235, 238. The same kind of oxide mixture will be used, but coolant will be normal water, right? This is the normal water which is used, normal water. But here, what is the thing is that in this, sorry, here coolant will be water there. No, here will be heavy water, which we are using for, sorry, coolant and moderator both are heavy water. ये एक basic difference है, इसको ध्यान रखना है. See, in India, when we started working with the next type of reactor, we developed this PHWR. Controller will be the same. I'll again, just 1 second. Let me explain, see if you remember that. The difference in both type of reactor vessel is that here coolant and moderator we are using normal water. In this case of pressurized heavy water, we are using heavy water. That is there. But this is costlier. Why costlier? Because you have to manufacture heavy water. Right? But this will be more efficient. Why? It can carry more heat, at the same time it can also moderate faster. Here we are using for moderation what? Normal water. Did you get that? Pressurized light water में हम क्या कर रहे हैं? Normal water को use कर रहे हैं, density का work कर रहे हैं. तो वहाँ हो सकता है कि moderation उतना efficient ना हो. Right? But in this case, we are using directly heavy water. So heavy water is capable of slowing down neutron. So heavy water is preferred. Why? Because heavy water is a moderator, is able to moderate. So we are able to control the reaction more in this case. So in India, when we started building next type of reactor, we first made this pressurized heavy water reactor. ये प्रेशर से काम करता है, ठीक है. लेकिन क्या इसका लिमिटेशन है, डिसएडवांटेज क्या है? इज कॉस्टली, बिकॉज यू हैव टू यूज हेवी वाटर. व्हाट इज एडवांटेज हियर? सिंस इट वर्क्स विद नॉर्मल वाटर, so we don't have to spend money for making heavy water. Now remember that European pressurized reactor, EPR, and sometimes you'll come across in newspaper VBER. Let me write here. I'm giving the example here. If you talk about this one, there's a one type of reactor you'll come across VBER 1000. ये काफी बार न्यूज में आया हुआ है. VBER जो है रशियन वर्ड है, इज अ रशियन वर्ड, इज नॉट अ इंग्लिश वर्ड. It actually means light water reactor. And what is the meaning of 1000? 1000 megawatt. It can generate 1000 megawatt power, right? But this is a light water reactor. Or sometimes you'll come across EPR. EPR stands for European Pressurized Reactor. So in Europe, let's say France, or the country like Russia, they have developed those kind of reactor which works with normal water and can generate very high power there. They are more efficient. On the other hand, what we have in India, this one, PHWR, what we have built, right, that is not as efficient. We cannot generate 1000 megawatt or higher, right? And another, what is the limitation? We are working with heavy water, right? So that's why we are trying to now get new technology from outside, so that in India, we can also develop pressurized water reactor working with normal water. We can do away with the cost in terms of heavy water. ये चीज़ है, ठीक है. This is a you can say second generation reactors. First generation reactor is boiling water. Second generation comes this type of reactor, right? Now, very few countries. I think if you talk about name of the countries, hardly I will come across 2 or 3 countries have got this new type of reactor developed. What is called fast breeder reactor. Right? It is not with every country has got this one. And India has developed this reactor, but today we are now slowly going into that. इसमें ये है, अब ये समझना है. Boiling water reactor, pressurized water reactor, all uses uranium-235, 238. But what I explained in the beginning of the classroom, it is 235 which undergoes fission. Right? 238 is wasted. 238 is wasted. Now, when we do the mining of the ore, so 235 and 238, right? If you take the ratio is 1:139. If you take 1 gram of ore, uranium ore, if you just take 1 gram of uranium ore, so what do you find is 1 part 235. and 1/40th part is the 238. But for power generation, we require what? 235. Right? We don't, this is not there. So what is the problem there? How to take care of this 238? And how to take care of this 238? So because this 238, we are having plenty in the nature. When we take from earth crust, we have more this one. So why not think of making a reactor which can use this 238? Right? And now here comes another advanced reactor technology, what is called fast breeder reactor. Right? There comes the concept of what? Fast breeder reactor. So till now I have discussed what? Boiling water and improvement of boiling water, pressurized water reactor. So now fast breeder reactor. Now what is so unique about fast breeder reactor is that is a reactor which basically breed. Here the word is what? Breeds. So I'll write in the sentence form here, generates fissionable material from, I'm using the word here, non-fissionable, which does not undergo fission, and that can be converted into fissionable material. So what exactly happens here? Uranium-238 is transmutated. What is called here? Transmutation. So is converted with the fast neutron. Here, one uses the fast neutrons, and this fast neutrons convert into plutonium-239. What I explained in the initial part of the class, 238 slow neutron will not undergo fission. So what is this fast breeder reactor does? It first converts uranium-238, which is non-fissionable, into plutonium. And plutonium will capture neutron. Here, it will capture what? Neutron, and will undergo fission. So here is what? Non-fissionable. It does not undergo fission. But plutonium can undergo fission here. So now imagine there is a reactor which can first produce plutonium from uranium-238. Now why it has been developed? As I've said here, there is more amount of 238 in the ore as compared to 235. And we wanted to make use of this 238. So we went to develop this one. So what is here? Now I'm coming to here. What is the fuel here? Fast breeder reactor uses fuel as plutonium and uranium-238. So what is the fuel here? Uranium-238, plutonium-239 oxide. Is it clear here? All these reactor uses what? 235, 238. But what it consumes? 235. It undergoes fission with 235. On the other hand, fast breeder reactor uses plutonium-239 and uranium-238. So from where the plutonium is produced? From uranium-238. So here the fuel is different. This fuel is different from here. Another very important concept which you have to know. What I've written in the reaction? Fast neutrons. It does not use slow neutron. So now my question to the class, is there any need of moderator? No. It does not require any moderator. Why? Because we don't have to slow down. We require fast neutrons. So this is one reactor which does not use moderator. Here we are using what? Moderator is heavy water. But here no moderator is required. So what will we use here? Moderator is not required. Why? Because we require to have fast neutrons. But it requires coolant. Now what is coolant here? Liquid sodium. It's cooled by liquid sodium. Right? Not with normal water, not with heavy water. It's cooled by liquid sodium. And controller will be the same, because when you have to control the number of neutrons, so you use the same kind of thing there. Boron. This is the technology worked out by our scientist. We wanted to make use of 238. We don't want to waste that one. Actually, if you look at all the 3-stage nuclear power program are interconnected. Right? We are all interconnected. You'll understand in today's class how they're interconnected, because we are wanted to make best use of the fuel. Whatever we have, we want to make best use of. But again, remember that this reactor is also dangerous. Why? It can be diverted for nuclear bomb. What happens there? It produces what? Plutonium. See, nuclear bomb, or nuclear weapon also is also made of plutonium, highly graded plutonium. So if we want to make nuclear bomb, we can take plutonium from here, enrich, and can make the weapons also. This one can divert also this technology, right? Because what is happening here, uranium is 238 converted to plutonium, and plutonium can be enriched and can be used for highly, you can say, dangerous plutonium-based nuclear weapon, which can be more lethal. It can be done, but generally, we have made it very clear that we will be using for civilian purpose, right? India has got both the program, and what we have done for peaceful use, for power generation, right? We have kept in a public domain. Any country can come and inspect. US can come and inspect what we are doing with those reactors, right? Even one of the organization, IAEA, can come and can inspect there. But there are few reactors which we have not kept on a public thing. They are used for making those kind of plutonium and all, which can be used for weapons, right? Exactly, government will never tell how many stockpile we have, how many weapons we have. But we are also having those reactors which are totally kept for military purpose. We are making the weapons, right? That part we are doing that. But others, what we come across in newspaper, are all for peaceful use. Here we are not diverting for any military program. It is only for power generation. Even the plutonium generated is again used up. It is not kept for any weapons program, right? There's another type of reactor what we have come across there, right? So what I'll do is that what I've explained here, few things in terms of reactor technology. I'll give you certain written part of it. As I said that you'll have a brief written part. Now this all exercise we are doing only just to keep in mind that in case if static area, any question comes in the exam next year, so at least you'll be aware of this reactor technology part of it. Okay, what exactly is fuel, what is the component, what is moderator, what is coolant. So that's why first I've given you the main point of it. Right, yes.
The pressurized heavy water reactor, what is the use of this U-38 oxide? Does it go fission?
Okay, very good question. I wanted to come to that, but initially I didn't go into that because I wanted to go stepwise. But since he has asked the question, I'll explain that. See, in both this type of reactor, boiling water reactor, we are using 238, 235. Here also we are using 235, 238, 235, 238. Now the question is what happens to this? This gets consumed. This gets burnt up. Why? Slow neutron will convert into daughter nuclei. What happens to this one? Remember that. So I'll write again the reaction there. What I explained in the class, uranium-235, slow neutron, barium, krypton plus 3 neutrons. What is this neutron? Fast. This has to be moderated here. So this fast neutron can do this also. This reaction what I've done. See, in this reactor, fast neutrons are also produced. But what we do, we slow it there using moderator. So the reaction can continue. Right? But where it is getting burnt, 235. But few of the 238 here can also convert into plutonium by this fast neutron as it happens in the breeder reactor. Are you getting that? See, here we are using mixture. So it may be possible that here these fast neutrons can bring about changes in the 238 also. This one. And this can become into plutonium. So what we can do? We can reprocess. Right? We can enrich and can use it in the second stage. Right? यहाँ पर क्या हो रहा है? ये तो use up हो जा रहा है. This will get consumed. This will get burnt. But this may also get converted into plutonium. And this plutonium we can enrich and can use it in the fast breeder. Next stage we can use there. So that's why this is what I have said what logical. What is logical? Whatever we are using in one reactor, we are using the second and third also there. So that it becomes used up. Plutonium also there. So few of those uranium-238, because the fast neutrons are also there. So it will also get, but not all. What I'm saying, not all. Few will be there. So why those few plutonium we can separate and then use it in the fast breeder reactor, that part. And remaining 238 will be again used up again in the process there. In the means that will again make the fuel and use it there. So it is also possible, what I'm saying, it is also possible that in this type of reactor, plutonium is also generated from the U-238. And that plutonium we can enrich and can use in fast breeder. right? And remaining U-238, which has not been converted, we can again make fuel and use in such kind of reactor as a mixture, 230 by 238. Huh. No, there what we are doing, we are there, when you're using uranium-238, we are converting to plutonium. Plus, the neutrons will produce. Fast, that will be fast. You can remember that. This neutron, what I have given, is will be fast neutron. Will not be slow. You're right, it is a fast neutron only. It will not be slow. So what is the thing is that we developed in a logical fashion, 238. But again remember that this is the reactor which will produce plutonium. It is more efficient to produce plutonium. हाँ हाँ हमारे पास ऑलरेडी है. हाँ 233, हाँ वो भी है. हाँ वही बात है. What is he saying that all this uranium we don't have enough in the country, right? Where we are having the mining, Jadukuda, that's where we are getting. We are very limited. But India has got more deposit of thorium. And what thorium can happen? I'll just what he has said. I write there. Thorium can be converted into uranium-233. As I have said here, uranium-238 can convert into plutonium. So why don't we use, when we have thorium of enough quantity, so why don't we use this thorium and convert to uranium-233, right? And then use it for any of the reactors here. The reason is that the thorium is not in a raw form. It is there in monazite sand, right? Which I have said that it is available in the monazite sands there. So what we require there? We require first the technology to extract thorium and the purification part. We are working on that very soon. Very soon you will come to know that we are also using thorium for this kind of reaction. It is also possible. Monazite is a name given. It's a kind of a, within the Kerala there, in the beaches there sands are there. The monazite sand. It contains thorium, plutonium, all these mixtures are. There's something called, what is called heavy elements. Heavy elements होता है, mixture होता है. उसमें कई सारे के elements होते हैं. What's called rare elements are said. And one type is a thorium also there, but not there. We have to first, from that sand, we have to extract the thorium. Then we can go for such kind of use there. So what is very important? We are developing the technology. India is working to develop this technology. Very soon, we will also have this one also. There is nothing wrong. What he says that we can use this thing here also. In fast breeder reactor also we can use that. We can use, in place of uranium-238, we can use thorium and convert thorium into 233. And we can go for power generation. That is also possible. But today we don't have the technology. We are working to develop that. ठीक है? लेकिन एक चीज़ है, ये क्वेश्चन 2012 में पूछा गया था. 2012 there was a question asked कि why thorium is better than uranium? Why thorium has to be preferred than uranium? Very soon it will happen. In coming years, we will be using thorium. We are working on that. Now tell me why thorium will be better than uranium if we go for thorium instead of uranium-238. So one, he has said what? We have limited uranium, but we have more thorium. So economically it is more better because we don't have to pay money to Russia or Kazakhstan or Canada or Australia and buy the uranium from there. We can use the thorium which is there in the country. So that will again, economic point will be very important. But the second point is that, see, thorium, again remember that, uranium we can use in this form, oxide form. But thorium is, again remember that, see, we can use directly uranium and can go for power generation. But thorium cannot be directly used. First we have to convert thorium into uranium. And then uranium will undergo fission. And that is it. But uranium undergoes direct fission. Another thing is that thorium produces less radioactive waste. Because all these processes also generate nuclear waste as compared to uranium. Uranium produces more nuclear waste. Again, thorium is more efficient because it generates more energy as compared to uranium. So I'll just tell you a point. What are 3 points? Let me say. First is that economic part. Thorium is more with India. So the economy aspect can be taken care. Second is what? Thorium cannot be directly used. Thorium has to first convert into uranium. And then it undergoes fission. Right? What I've said, third aspect, that thorium produces more power, more heat as compared to uranium. So it can be more efficient. And what is fourth point I've said? Thorium generates less radioactive waste. Thorium generates less radioactive nuclear waste as compared to uranium. So waste disposal will not be a problem with thorium. थोरियम के साथ प्रॉब्लम नहीं होगा. हाँ.
Thorium is converted into uranium. How can it produce less uranium?
No, because thorium is radionuclide which is produced less. Say thorium produces less radioactive waste because the radionuclide which will generate will have those kind of half-life which will be shorter than uranium. So uranium takes more time to go into normal kind of thing. That is a disadvantage. What is disadvantage? More generates energy is less there. Radioactive waste is less. I'll come to that now. Right, now see here. See here, if you look at advantage, for example, if you look at advantage, so what is advantage? More energy generation, because it will generate more energy there, and less waste will be there, nuclear waste. That's advantage.
Can't directly be used as a radioactive.
What that is it. This one is what is correct. What he's saying is very true. When it is cannot be converted into uranium directly, we cannot use it. We have to first convert uranium-233 is one of the limitation, right?
More efficient than 35 or 38.
All right. What is the thing is that, see, 235 and 238 are naturally available. The 233 is generated artificially. That is the thing that what is there? This is what we are saying about. This is naturally available. When we take ore, we get 235, 238. In the ore, will not get 233. This only happens in the reaction. In the reaction, it happens. That part.
डायरेक्टली यूज ही नहीं कर सकते थोरियम को तो इस
नहीं डायरेक्टली करने का मतलब है थोरियम को अगर हम स्लो न्यूट्रॉन में पास करेंगे तो वो ब्रेक नहीं करेगा. यानी कि पहले थोरियम को हमें यूरेनियम 233 में कन्वर्ट करना होगा, फिर वो न्यूट्रॉन के साथ स्ट्राइक करके ब्रेक करेगा. तो ये इसका एक लिमिटेशन है, प्रॉब्लम है.
जो हाई हीट और रेडियोएक्टिव वेस्ट का जनरेट करते हैं
हाँ.
और इसका फिर फायदा ये थोरियम करेगा उसका या फिर यूरेनियम 233 का एडवांटेज. मैं तो
हाँ नहीं, ये आप कह सकते हो. एक्चुअली एडवांटेज इसी के साथ में यूरेनियम 233 का ही एडवांटेज. लेकिन यूरेनियम 233 क्या आर्टिफिशियली प्रोड्यूस होता है. ये नेचर में अवेलेबल नहीं होता है. ये केवल तभी प्रोड्यूस होता है जब हम थोरियम को कन्वर्ट करते हैं, फास्ट न्यूट्रॉन करते हैं, तभी कन्वर्ट होता है. राइट. नेचर में क्या अवेलेबल है? 235, 238 है. ये केवल रिएक्शन में ही फॉर्म होता है. यू कैन से ये इन सिटू जनरेट होता है. इन सिटू इन रिएक्शन इट इज जनरेटेड. इट इज नॉट नेचुरली अवेलेबल.
Excess of uranium used for the fast breed reactor.
This one, so excess of? Uranium 238 we are using for fast breeder reactor. 238. We are using that because since we are having more of 238 and we don't want to let that 238 waste, so we are using 238 here and that gets converted. So इसलिए whenever we use any reactor vessel हमेशा mixture होता है. तो plutonium भी होता है 238, but actually क्या है? 238 is converted into plutonium and then we'll use for plutonium will undergo fission reaction. Yes. Somebody was asking the doubt. See, moderator here, in this part, we don't use the moderator there as such. In this one, see, is this fast breeder reactor? Sorry, the precise water reactor. Moderator used in the same way. Let's say, for example, PHWR. So in PHWR, this pipe which I have drawn, it uses heavy water only. But again, moderator also, both twice. Remember that. In the PHWR, heavy water deuterium oxide is used both as coolant and moderator. It's same pipe. It undergoes the same one. We don't use it separately. It undergoes same thing. But again, remember that if any question, statement type or direct is asked in any exam and ask you moderator, so you should always have heavy water. Right? Heavy water is preferred as a moderator. Right? Though heavy water can also be used as coolant. But what is the prime role of heavy water? Moderator. Right? It was asked in the UPSC exam 2011. What is the role of heavy water? And there was option given, coolant, moderator. So we can use for cooling also. But actual use of heavy water is only for moderation. Moderator is the main part of it. Since in this type of reactor, fast breeder reactor, we don't require slow neutron, we require fast neutron. So we don't use any moderator there. Right? वहाँ पर liquid sodium से हम cool down करते हैं. That part is there. Right? So it will become more clear when I give the notes. It will become more clear into that. And then I'll show you one animation also there. You'll understand how the reactor works there. You'll be able to understand from all the aspects there. Now, first you write a boiling water reactor. Just give a heading, boiling. I have given the main point, but I'll put in a paragraph there, boiling water reactor. Now you write it. Inside the BWR, inside the BWR, boiling water reactor, BWR, inside the BWR vessel, 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 comma, a steam water mixture is produced. Inside the boiling water reactor vessel, VESSEL, common, comma, a steam water mixture is produced. A steam water mixture is produced when very pure water is produced, when very pure water, in bracket reactor coolant, very pure water, in bracket reactor coolant, moves upward through the core, absorbing heat, moves upward through the core, absorbing heat. Right? So what I said here, in the boiling water reactor, it produces a mixture of both. And the steam what is generated, that will be separated. And that will run the turbine, mechanical to electrical. Right? Now one more sentence you can write. After giving full stop, you can write. You can write this. The steam water mixture, in the same paragraph, the steam dash water mixture leaves the top of the core, and enters the two stages, TWO2 stages of moisture separation. Enters the 2 stages of moisture separation, comma, just give a comma, same sentence, moisture separation, comma, when water droplets are removed, before the steam, is allowed to enter. I'll repeat this, where water droplets are removed before the steam is allowed to enter turbine generator. Right? Simply turbine generator. Enter the turbine generator. Right? Give a full stop there. Enter the. See, remember that ये होता है stages में होता है. तो हमें उतना engineering aspect नहीं जानना है कि exactly क्या होता है. बेसिक कंसेप्ट ये पता होना चाहिए कि अच्छा बहुत हाई टेम्परेचर होता है तो ये मिक्सचर होगा, स्टीम को हम सेपरेट करेंगे, स्टीम लाइन होता है, स्टीम को पास कराएंगे, फिर टरबाइन जनरेटर है. बाद में क्या होता है, स्टीम को कंडेंस भी किया जाता है, वो वाटर में फिर वापस होगा. लेकिन प्रॉब्लम क्या है, ऐसे स्टीम को हम वापस दोबारा यूज़ क्यों नहीं करते हैं? रेडियो एक्टिव होता है. क्यों? क्योंकि ये कोर से पास कर रहे हैं. हम डायरेक्टली क्या कर रहे हैं बॉइलिंग वाटर रिएक्टर में, कोर के अंदर ही हम उसको स्टीम बना रहे हैं. तो वो जो वाटर जो है वो क्या है, रेडियो एक्टिव होगा. ये प्रॉब्लम है. So earlier type of reactor, old generation reactors followed this kind of a technology, right? But we also developed in India first this type of reactors there. But again, remember what I've given here: normal water, heavy water, boron, and all this part comes, right? Now I'm coming to the pressurized water reactor, right? I'm coming to the pressurized water reactor part. Now next you can write there, pressurized heavy water reactor. First you give the call heading there, PHWR, pressurized heavy water reactor. Now you can write this, PHWR. A PHWR, pressurized heavy water reactor. I'll come to light water also there, but first pressurized heavy water reactor is a nuclear power reactor. Comma, commonly using unenriched natural uranium. Commonly using unenriched natural uranium as its fuel, comma, that uses heavy water, in bracket deuterium oxide, bracket closed, as its coolant and moderator. as its coolant and moderator. Right, give a full stop. Now same paragraph. The heavy water coolant is a very important point I am giving. The heavy water coolant is kept under, the heavy water coolant is kept under pressure, is kept under pressure, comma, allowing it to be heated, kept under pressure, comma, allowing it to be heated to higher temperatures, allowing it to be heated to higher temperatures without boiling, higher temperatures without boiling. Right, give a full stop there. So, as I said, it generates what? Superheated water at 250 degrees Celsius, but will not convert into steam. तो यहाँ पे क्या होता है, दो लूप होता है, एक प्राइमरी लूप होता है जो कि ये मैंने ड्रॉ किया है, उसके अंदर क्या होगा, हैवी वाटर ही पास करेगा जो कि कूलेंट भी करेगा, मॉडरेट भी करेगा, और एक दूसरा साइकिल होगा दैट इज कॉल्ड सेकेंडरी लूप वेयर द हीट विल बी गेटिंग एक्सचेंज्ड, दैट विल जनरेट स्टीम एंड स्टीम विल मूव द टर्बाइन जनरेटर. That kind of concept is there. So after giving full stop, you can write. Now, very important point. I same paragraph write. While heavy water is significantly more expensive. While heavy water is significantly more expensive than ordinary light water, comma, it yields greatly, GREATLY, greatly enhanced neutron economy. It yields greatly enhanced neutron economy, comma, allowing the reactor to operate without fuel enrichment facilities, allowing the reactor to operate without fuel enrichment facilities. Right, give a full stop there. So what is the thing there? Though it is costly, why? Because you have to manufacture heavy water. But what is the advantage? Heavy water is a moderator. So it can control the number of neutrons. So that advantage comes there. So that is where always the plus and minus. There will be advantage also, disadvantage also. That comes into that. Right? Now you can give it pressurized light water. This is heavy water I have given. Now I am coming to pressurized light water. Now pressurized light water, you can write this. A pressurized light water reactor uses normal light water as the reactor coolant and moderator in the state of high temperature and high pressure. In the state of high temperature and high pressure, not boiling, same sentence, not boiling in the reactor core, and sends SENDS, and sends the high temperature and high pressure water to steam generators to generate steam for a turbine generator. Now one more sentence after giving first stop you write. The reactor coolant is pressurized so that it generates higher density it generates higher density and generates higher density and acts as moderator So whenever you read about it, it will give you that the main purpose of pressure. But what I said here, see, that's what first I made what kind of distinction. If any time when you revise your class notes, it will become very clear that what is the role of each of the component. I have written here what coolant and moderator both are water, and here the same water at high pressure can be made more dense, and because of dense it will slow down the neutron. Right point of vision. But here on the other hand we are using heavy water. There's a difference there. Right? So that's what I said. Today European countries like France, like Areva, there's something called Areva, if you are there, how much it can generate? 1650 megawatt. These are based on light water reactor. ठीक है, अब मैं आपको बताता हूँ, बहुत पहले जो बुक्स हुआ करते थे साइंस टेक का, they used to only talk about PHWR. They didn't used to talk about PWR. But now, what I've said in the very first class, indigenization. So now we have developed pressurized water reactor also, light water reactor. Why? Because we have got the technology from Russia, like Kudankulam. One good example of this VBR is the Kudankulam reactor. So now when you come across magazine or newspaper and they mention the word VBER, they should directly come to your mind, it is a pressurized water reactor working with normal water, not with heavy water. Right? That should come to your mind. The technology part, concept part I've explained. Right? Now I'm coming to fast breeder reactor, FBR, the kind of reactor. So now give a heading there, fast breeder reactor. Now we can write the fast breeder reactor. It is a fast breeder reactor. Fast breeder reactor uses fast beam of neutrons. A fast breeder reactor uses fast beam of neutrons to irradiate uranium-238 to irradiate IRRADIATE to irradiate uranium-238 into plutonium-239 Give a full stop there. In this reactor, comma, no moderator is used. In this reactor, no moderator is used. Give a full stop there. There's liquid sodium. Liquid sodium is used as coolant, material, which exchange heat with steam generator. Which exchange heat with steam generator. Right? Give a full stop there. Steam generator. But what I said here, I have also said that we can also use thorium. So later stage, maybe the FBR can be used for thorium also there. And what I have said that thorium will be irradiated into uranium-233. That is also possible. But today, since we are still working with thorium, so we have now kept fuel as 238 and plutonium as a mixer oxide.
It can catch fire in low temperature.
But no, it can. What is saying that you know that from chemistry, the liquid sodiums are stored in the kerosene or something of that. Because outside air, if you keep it, it will get there. So again, that is kept in a controlled condition there. Liquid sodium is liquefied form. There's a high pressure. It's used in a high pressure liquefied form. Otherwise, it will go to the higher temperature, catch fire. So it will be very difficult to run this process there. That comes there, right? Now I'm coming to this part. After this, I'll show you the documentary part. Now our BARC scientists have gone to develop another advanced reactor, what is called thorium reactor. And the name is here AHWR. I'll first write the main point here. Advanced heavy water reactor. Now prototype has been developed. Here we have developed the prototype, but still we are working for commercial aspect of that heavy water reactor. Advanced heavy water reactor. So from the name you can figure it out, heavy water. Again the word heavy water is there. So what is fuel here? See here, fuel is thorium uranium mixture. So here it can be thorium-232 And what I said, uranium-233 can be generated there. But we can also use, remember that, in the same reactor, we can also use thorium-plutonium mixture also. Because thorium can, again, transmutate in stages and can generate plutonium. But actually, it is what is the main aspect is thorium. This is the main aspect, oxide of that. Now, in this case, again, remember that moderator and coolant is the heavy water. We are using heavy water as, again, for moderation purpose and coolant purpose. But the design of this reactor is a kind of a pressure tube kind of reactor. It's a vertical type of tube, right? Generally, reactor, what you find is a broad kind of, it's a very different design is there. Again, this is heavy water. And controller is the same element. Boron, we are using boron as a preferred material. Now, the advanced heavy water reactor, you can write about this. I'll give you the part of this.
Why we are able to do 233? Because it can be produced only by the reaction of.
But that's what happens. We'll directly use thorium here. This is directly use thorium only. In the process, it generate. And sometimes what I've said is, if you want to use, one more thing is that, I'll tell you that. Thorium, just let me add here. Thorium has two isotopes. Like uranium exists at 235, 238 in nature. The natural thorium is also of two form, 230, 234. So what can be done here? This 234 can be converted to 235. But this will become into what? 233. But 233 is what? Not naturally available. What is naturally available? This one. Okay? 238 here. 235. Why don't we? No, actually this reactor has been designed to use the thorium as a primary fuel. 235. And this, that's what I said. This uranium, what I said in the beginning there, directly we cannot break into thorium into two parts. We always first convert into uranium. Right? So here, though we are using thorium, but actually in the reaction vessel, what will happen to generate uranium? Did you get that? Directly uranium, thorium will not be there. Thorium will be? करेक्ट. हाँ फिर ये इसमें क्या करेंगे हम लोग थोरियम को यूज करेंगे. ठीक है, तो थोरियम को यूज करने पे क्या हो रहा है, प्रोसेस में यूरेनियम जनरेट हो जाएगा और यूरेनियम का अंडरगोज फ्यूजन होगा. हाँ, एंड व्हाट इज द एडवांटेज इज दैट इवन इन दिस यूरेनियम व्हिच इज देयर वी कैन फीड इनटू द फर्स्ट स्टेज आल्सो. दिस वन जनरेट हो रहा है. तो इसका अब ऐसा समझो आप, वी हैव थ्री टाइप ऑफ रिएक्टर, PHWR, FBR, AHWR, and all these three are interconnected. For example, what we make here plutonium, कुछ ऐसे 238 plutonium convert हो जाएगा, so we can use it in the FBR, fast breeder reactor. In this reactor we are having thorium. Thorium can convert to uranium, and even this uranium, if you want, from thorium we have made the uranium. If you want there, we can go for this reactor also. So actually that logic has been applied, but actually this reactor will use thorium completely, and advantage is that it will burn more thorium. That means thorium will convert to 235. Your question is right, why don't we, this uranium 235 is this. But actually what is the main concept has been kept, we take the thorium oxide and then use in the reactor, and in the process generate uranium, and the uranium undergoes fission. That means with the slow neutron. That's what, now you understand. Here in this AHWR we are still using the moderator as heavy water. Why are you using moderator as heavy water? Because the thorium will convert into uranium, and uranium will undergo fission only with slow neutron. There we don't require fast neutron. Did you get this? Huh.
With fast neutron, it will penetrate and pass out with the...
No, that is possible there. But actually the main purpose is that we have to use more and more plutonium, and plutonium undergoes the fission. That's part of there.
No, but if you provide moderate neutrons, then only it will absorb and...
Absorb in that case. Huh.
Fast neutrons will pass out.
No, fast neutron here means will go to that high speed. Because otherwise the reaction will not be over there. Still there, part of it. But actually I'll tell you that, comparatively fast. But actually what is the thing here? Remember that the concept is like this. यहाँ पे जो थोरियम हम यूज कर रहे हैं तो वो कन्वर्ट होगा यूरेनियम में, and this uranium undergoes fission, and but this fission will be only controlled with the slow neutron. So we require a kind of moderating element here in this case. But there, fast breeder reactor, what we are using uranium-238 plutonium as a mixture. So when we are saying fast neutron, so fast neutron doesn't mean very high energy. It will be such kind of energy which will be able to convert plutonium and break the plutonium into daughter nuclei. उसको convert करने के लिए. हाँ.
यूरेनियम 233 का ऑक्साइड क्यों यूज किया हमने?
हाँ, ये ऑक्साइड यहाँ पर क्या है, हम इसको निकाल सकते हैं, उसको प्यूरिफाई करते हैं, वहाँ पर लिखा जाता है. कुछ हम हमेशा ये याद रखना है कि whenever we make, we will not use it entirely the same thing there. So what we'll do, we'll make uranium-233 and mix with the, but actually the higher percentage will be thorium. This will be lesser percentage.
पिछले वाले में हम यूज कर रहे थे U238 करके उसको प्लूटोनियम में
प्लूटोनियम कन्वर्ट कर सकते हैं वहाँ पर. यहाँ पर थोरियम ज़्यादा कंसंट्रेशन में होगा, यूरेनियम-233 कम कंसंट्रेशन में होगा. हाँ 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 हाँ, right. No, it's not like that because the thorium, this which undergoes there, no, uranium-233. So uranium, as you said that uranium-235, 233 generate more kind of things there. But actually, what happens, they're neutron in such a way that will make it to such a radioactive nuclei, which will be less other part, not of this one. Because actually, what happens, the neutrons are still there, but will make those kind of nuclei, radioactive nuclei, daughter nuclei, which will not be that kind of persistent kind of radiation. Will be short lifetime, so that it can be taken care of it. And again, remember that what we have developed is not very efficient. Not very efficient means it can generate only 300 megawatt, not 1000 megawatt, not 1500, just 300 megawatt. Only prototype has been developed. I'll give you the part. I have taken from the BARC document. I'll just write there. It will become there. Now you can write this. AHWR, right? ASWR is a 300 megawatt. I'll give you all the point, all the advantages, everything I'll give you there. Now you write this. AHWR is a 300 megawatt, comma, vertical is a 300 megawatt, comma, vertical, comma, pressure tube, TUB, pressure tube type, comma, boiling light water, cooled, 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 and heavy water moderated. Boiling light water cooled, comma, and heavy water moderated reactor. Heavy water moderated reactor. Now to give full stop, you can write. The reactor incorporates a number of passive, PASSIVE, passive safety features. Incorporates a number of passive safety features to reduce passive safety features to reduce environmental impact. To reduce environmental impact. You have full stop there, same paragraph. It possesses PUSSES, possesses several features. It possesses several features, comma, which are likely to reduce its capital, and operating costs. It are likely to reduce its capital and operating costs, comma, such as, give a dash. Now write point wise, what all features it has got. Number one, first, using heavy water. Number one, using heavy water at low pressure reduces. Using heavy water at low pressure reduces potential for leakages. Using heavy water at low pressure reduces potential for leakages. Now, number two, second, recovery of heat generated. Recovery of heat generated in the moderator. Heat generated in the moderator for feed, FWD, feed water heating. For feed water heating. I'll explain everything. Feed, FWD, feed water. What is feed water? I'll explain there. Heating part of that. Now, just let me explain here. What is said here? I'll give you more point, but first to understand what is there. Is a feed, water, heat, heating, heating part of it. Now, what is there? See, here it is a tall pressure tube type of reactor design. Now, what is the principle here? It uses as a moderator heavy water, but here the pressure is not very high. Here we use what? High pressure. We use the low pressure. Now, why we maintain the low pressure? So that it should not result into leakages, because it's not a broad type of reactor, but a tall type of reactor, tube-like type of reactor. So that is what it comes. Second is what? It's 300 megawatt reactor, and water, again, if you look at the water for generating heat is a normal water, which is used in a boiling water cooled type of this. But for moderation purpose, we are using the heavy water. Now further, what is said here is that, in this case, all the major components, now see, if you make broader type of thing, it requires more cost, because you have to set up the more unit there. It just like you can say, AHWR is a kind of a, again, modified form of boiling water reactor only. But it uses water and is a, you don't require more parts. It generates the steam, and that steam can run the turbine generator. Right? Whereas on PHWR, what happens? You require the reactor vessel. You have to pass the heavy water as coolant and moderator. Heat has to exchange to another one. It will go to steam generation. It will run the turbine generator. All this cost and the kind of layout is get minimized or eliminated in the case of AHWR. Because it uses a single unit. You can say it's a single unit, integrated one, and which can generate power. So that's why it's said cost efficient. If you look at, I've given the word cost part of that. One more point you can write. One more in the same point you can write. Elimination of is a very important point. Elimination of, next third point, elimination of major components. Elimination of major components and equipment. Major components and equipment such as primary coolant pumps. Such as primary coolant pumps and motors, comma, associated control and power supply equipment to run these pumps, run these pumps, saving electrical power required. Saving required electrical power. Right. So whatever the power is for running those kind of things, the motor, the coolant, all this one is eliminated. Right. So this is just a kind of, you can say, initial part we have developed. But what I've said in the very first class, we are still in the first stage. See, our power reaction is still there. Right? FBR we have developed at Kalpakkam. If you recall, I have said in the class that Indira Gandhi Center for Atomic Research we have developed, but still we are generating power from using this kind of reactors. So it will take time. Slowly India is moving to the second and third stage. Right? So why you can say that when India has got so much of thorium, we should have move much faster. Reason is that we are trying to build the facilities. Right? And very soon in today's class, I'll go into the concept of nuclear fuel cycle. Because for power generation, it's not that only building reactor. If you just make a reactor, it will not work. It requires enrichment facility, reprocessing, mining, exploration. A lot of ancillary operations are required. That's why we have not started thorium reactor, this one, though we have developed. But if we build up all the infrastructure, once India has built the infrastructure, so we'll go for power generation using this one also. So slowly we are moving to that, right? We don't, see, we have, even look at, again this will mixture part of the 230, 234. More you'll find again the 232 there. Right, that is what we have. If had with 234 more, then we would have basically generated 235, we ran in 235, it would have helped us. 232 is more, is again a mixture part of it. But yes, one advantage what we have, monazite sands, we have more in the country. In geography, have you covered that one, which all part? Okay, what I said, maximum is the Kerala. But we do have a deposit in Tamil Nadu and also in part of the Gujarat, then part of Mahanadi, part of Cuttack. This is part of Odisha also we have. Now all this information, now I'm going to open that report. You'll see that where in India, what type of we have got that. So what I'll do, first I'll play this documentary, right, infotainment, and then I'll come back to the concept. So let us go into that part of here. वो इसको on करना होगा. Again, remember that this is a static area which I have to cover in the classroom as a kind of concept there, given the fact of the examination which requires all such kind of inputs there. Other things I have already mentioned, where we have nuclear parks, what we are going to build, ambitious nuclear program. So all this part you have done that. And then try to please try to link this area with your IR also there. Have you got your IR class done here? Ajay, there you learn about NPT, CTPT, right? What is NPT? Nuclear non-proliferation. So which all countries have not signed? Now, you know there's again current news is coming. What coming in current news? North Korea. It has been now, again has been put under sanctions by UN. Right, the North Korea signatory of NPT, Nuclear Non-Proliferation Treaty? Is it signatory? I'm asking signatory. North Korea joined and then walked out, came out of it. But right from beginning, 3 countries, right, India, Pakistan and Israel have been non-signatory of NPT. Right, and you can add one more, this division of Sudan. Sudan, North and South Sudan. They have South Sudan. That comes. But right from beginning, these 3 countries are there. North Korea joined and then violated, came out of the treaty there. Right. So now again, another sanction has been put up by UN over North Korea. Is now all this comes. So you'll often come across about nuclear safety, nuclear security. IR aspect will also come. Bilateral agreement, multilateral agreements, already part of it. So let me go into this one. This video is atomic energy. Okay, now you'll get to understand every aspect. First time playing here, nuclear power in India.
This is a view you'll see in few countries today, a nuclear power plant under construction. It's one of 6 now being built in India, with another 13 to come.
In addition, we have an ambitious plan that through the international civil nuclear commerce, we would go for additional 40,000 megawatt installed capacity, which could be, let us say, 40 plants of 1,000 megawatt each.
It's to help power megacities like Mumbai, already short on electricity.
There are large parts of India where we're not able to provide electricity for all 24 hours a day. And we have to resort to power cuts. And for several hours at times, we're not able to feed electricity to houses or industries. There have been occasions when students couldn't get light to study even when their exam is tomorrow.
India generates about 80 watts of electricity per capita. That's 1 light bulb's worth per person. Even with all electricity options on the table, the country faces enormous energy challenges. By mid-century, the population is projected to hit 1.5 billion.
India, and actually all of us, really want that 1.5 billion to have a higher level of economic development than the 1 billion do right now. So they're just going to need a lot more energy and a lot more electricity. Now, at the moment, they get about 2/3 of their electricity from coal, and you can't expand coal forever. Plus, it's dirty. It's not good for the locals. It's not good for the planet. Nuclear, they know. They're good at it, and it's got a lot of expansion potential.
Finding innovative solutions is vital if the country's going to achieve energy security. Fast breeder nuclear reactors, like this one being built in Kalpakkam, are part of that plan.
You would realize that these reactors are going to be extremely important because we can use uranium resources at least 60 times more efficiently. And we can also bring down the toxicity of the nuclear waste, especially high-level nuclear waste, to a level where after 500 years the level of this toxicity would be equivalent to a natural radiation levels. So these kind of reactors have much for the world to look forward to from the sustainability and the nuclear waste management and public acceptance point of view.
India has scant uranium resources but rich deposits of thorium. It hopes one day to use thorium to fuel the reactor. But it's not a fissile material and a huge scientific challenge.
Very important for country, the pride of the nation, based on very high end of the technology, and this will pave way for making far greater reactors for the world.
Thorium is not a totally fissile material. So that is what requires technological challenge. How you make the use of thorium in such kind of reactor. So this is what you find here. Now this prototype AHWR, you'll see here how it exactly this experimental thorium reactor has been worked out there.
What awaits me is a very unique experience, a visit into the core of a nuclear reactor, the latest and the most sophisticated nuclear reactor of India. We are not allowed to show the exterior of this building, else the location be disclosed. This sunny glow reflects the mood at India's newest reactor. All that you see has been mastered indigenously by scientists, often against great odds like international sanctions. This is an experimental reactor that may hold the answer to India's chronic electricity shortage. Currently, all power reactors need uranium, of which India produces very little and cannot import enough of. So the Department of Atomic Energy is banking on this, thorium. In its raw form, it's available in abundance on the beaches of Kerala. India has a third of the world's known reserves. After refining, it is turned into these pellets. These are then enclosed into special steel tubes to make them into fuel bundles that power a reactor. And that's where the new reactor comes into the picture. Scientists are using it to find out how the thorium behaves, further ensuring that every ounce of energy is squeezed out of uranium and thorium. Data from this new reactor will be used for building a super safe thorium reactor that the country hopes to build in the next 5 years. If everything works out as planned, there could be a huge network of thorium-based reactors that could satiate India's energy needs for the next 250 years. NDTV was allowed to visit this unique atomic laboratory merely a few days after it became fully operational, or as nuclear scientists say, went critical. It was also the Atomic Department Chief's first visit. The usually reserved Anil Kakodkar was clearly overjoyed.
And he told me that the level at which criticality was reached was so close to the prediction, so it is embarrassingly close.
Indian scientists should obviously be happy with this achievement, but joining them in their celebration and applauding this achievement is also the global nuclear community. Harold McFarlane, a former president of the American Nuclear Society, told NDTV that he expects that this would be the best facility in the world to obtain benchmark data for thorium-powered reactors. And it can be a wonderful research tool for training new generations of scientists. So why is this reactor generating so much excitement? Because it's only for experiments. It generates very little power, barely enough to light a single bulb. unlike most other research reactors, this facility is unique as the entire nuclear fuel itself can be modified or replaced on demand. To help understand the nuclear chain reaction in a thorium environment, the reactor has been designed so that scientists can enter the facility to conduct experiments at will. There's supposed to be no radioactive threat to humans. Nevertheless, there are precautions like this massive door and safety tests. Once we are inside, a quick check shows there is zero radioactivity. This new facility is the real test bed for assessing all future nuclear fuels of India, not just thorium.
Actually, you ought to have been here.
Who would know more about future nuclear fuels more than V.K. Raina, a nuclear engineer for the last 38 years?
How many people are doing anything with thorium in the world?
Well, right away, I don't think too many countries have too many compulsions to look at thorium very seriously. But given the fact that India has very limited resources of uranium available, so we have an urgent need to look at thorium, and we are seriously looking at thorium, and that's why.
So is thorium the solution for long-term energy security
Yes,
for India?
if we are looking in time frames of 100 years or 150 years or 200 years, certainly thorium will have a great role to play in the energy security of the
150 years
country.
is too far. Why worry about it just now?
Exactly, that is the point. If you look at various energy sources, look at the availability of hydrocarbon-based fuels. If you see at the current rate of consumption, maybe we don't have more than 75 to 100 years. Beyond that, we have to go for sources which are available to us. And thorium is one major source from which we can tap energy.
And it's one of its kind in India?
It is, yes. It is, certainly it is. Why? It is one of its kind in the world also.
One source for India's hunger for uranium would have been the international market. But for India, as of now, it is a forbidden fruit. So, as the Indo-US civilian nuclear deal makes little or no progress, the only sustainable option is right here. I am standing right on top of India's finest and latest nuclear reactors. This is the place where India will test its future fuel thorium. Deep inside India's nuclear weapons lab, the Bhabha Atomic Research Center, with camera person Ranjit Viswas, this is Pallav Bagla reporting for NDTV.
Such documentary you are able to understand more. And another thing is that why I'm going to such reports and the documentary part, so that you know that what exactly is happening right now in India. Because when you read textbook or when you read there, you may not get the exact picture of that, exactly we have or not. But now you can make it from the documentary that we have developed the reactor. It's only the matter of time when we go for power generation, right? So this was the NDTV documentary which talks about thorium reactor ASWR. And you have seen that is a vertical type of a reactor. Though clarity was not that, it is a not high definition video, right? But you can make it out there. Now what I'm coming here, when you read India Yearbook, right? When you go to the India Yearbook chapter on science and technology, there clearly is given about this concept of nuclear fuel cycle. Though what I explained in the classroom about boiling water reactor, precise water reactor, fast breeder reactor, ASWR, but you'll also find that. And you know that I have even said last time also, and I'm mentioning today's class also, that such sources, right, are potential sources from where the question can be picked up. Is again the thing is that till yet in the last 10 years, questions have not come from this kind of area what we are learning in the classroom about nuclear fuel cycle or reactor technology. UPSC has not asked any direct question. So let's say in the coming year exam, 2018 exam, you expect one question from this kind of reactor, so at least you are aware and you can get to the correct answer in the question there. Let me come to this concept of nuclear fuel cycle, NFC. So I'll write the points and I'll supplement with that exact part what is given in India Yearbook. I'll open that report also. You'll see where it is given in the pages and paragraphs. But first understand, what do you mean by the term nuclear fuel cycle? So the first thing is that it refers to processes processes required for power generation. What are the steps, processes required for power generation using nuclear reactor? Using nuclear reactor. So that is referred to collectively as fuel cycle. Whatever reactor we are using, that based on that. Now it is divided into two stages. What is called front end cycle and back end cycle. There are processes which are linked with front end. I'll explain with the diagram there. And then second is called back end cycles. Now let's understand here. Today India has developed all these operations steps required along with the R&D, research and development organization, public sector undertaking, companies, government companies and facilities. We have built up that. Now it starts with that. The first stage, which I'm writing here in the nuclear fuel cycle, that is referred to exploration survey. So what I'm writing here, survey and exploration of resources. So what we require resource here? Uranium or thorium. Okay, where in India we have a deposit of uranium or thorium. So first task comes, we have to survey and explore, right? So this is done by, now I'm writing the name of the company, it's called Atomic Minerals Directorate. There's a directorate there. This work is done by Atomic Mineral Directorate, which is located in Hyderabad. I've written a short form, HYD, Hyderabad. In Hyderabad, we have this particular R&D center, you can say, Atomic Minerals Directorate. It is in charge of what? Survey and exploration of uranium in the country. So right now in the beginning, the first place which comes to everyone's mind is Jaduguda. Right? Jaduguda is a place. But we still have many other places where uranium deposits have been now found out. In recent past, we have located, there are other states, other places in India where we do have uranium deposits. So if you look at the places there, right, I'll just take you to the map there. There's a nuclear map of India. So there you'll find that, where on the part of this is a place where we are going to have power generation, but let me just go into that part. Okay, now anyone in the classroom who wants to just mention about that? Okay, where all places in India we do have uranium deposit. Jaduguda is the one where we are doing the mining, but there have been many places been found out. So this is given India Yearbook also, but first let me write here. If you look at the uranium deposits, because of this kind of a division, there's a directorate which I found. So we have right from the beginning what? Jaduguda. Where is Jaduguda located? Which part of Jharkhand? District of Jharkhand. Can you name those who come from those, which district of Jharkhand where such uranium is found? Jaduguda is a place of where we're doing the mining there. We have the mines. That is called Singhbhum district. There is something called Singhbhum. East Singhbhum, West Singhbhum. The Singhbhum district in Jharkhand, where we have not one place, there are a number of places where such uraniums are found there. But now I'm coming to another place. And I'm writing it because this is given in the report of, annual report of DAE also. Tumla Palle. And you will be, let me provide this information. You will be surprised to know that we have started mining also there. Tumla Palle is a part of which state? Andhra. Is a part of Andhra Pradesh. Right, is a, let me write it, AP. And AMD, this one, has found out the uranium deposit and already we have started mining. So you can say our second type of mines in India apart from Jharkhand is now in Andhra Pradesh, Tumlapalle. It has come in the newspaper also, right? Now places we have found where we have not started mining but there are deposits. So I am now giving the place, Rajasthan. In Rajasthan there is a Rohil. Rohil in Rajasthan, that is a part of Sikar. Near Sikar district, there, Rohil, there we have found uranium deposits. We do have in that. Then comes very, very important name. Two names I am writing here. It is given in the Vision IAS material also. Domia Siat, right, and Wakhin. So let me write here. Wakhin and Domia Siat. So where, which state? Is located in Meghalaya. Meghalayan plateau. You know that Garo Hills, Khasi and Jaintia. There's a part of Khasi and Garo. There is a deposit found in these two places called Wakhin and Domiasiat. So we do have what? Uranium deposit. But again, Meghalaya is, you know, that forest state and all this part. So other states like Meghalaya, Rajasthan, we do have found in Madhya Pradesh also there, Karnataka also there, like Gwalior Basin. There have been deposit of that. In Karnataka, Dharwad and all this. Again, the deposit has been found. But these are the places where we can start the mining part, right? What comes the next in the cycle? First, we have to do the exploration. And we can locate where in India we have got uranium deposits. So what comes the second one? Mining. The second operation, it requires a mining, and I'm writing another process called milling. We need to mill. Milling means what? Purification of the ore. Because the ore which will take out from the earth crust, now then again we have to purify with all the impurities, has to be removed. Now milling operation required. Now there is a company for this, what is called UCIL, Uranium Corporation of India Limited, that is located in Jaduguda. Uranium Corporation of India Limited, this is a company which has right from beginning has been involved in mining operation, like taking uranium out of the earth crust, UCIL. Now I'll provide you the few names of the place there. Let me just, isko band kar dena, taki I can put the extra information on the other side. One is the Jaduguda. Apart from Jaduguda, there are other mining areas also, mining sites, which is given in India Yearbook also there. Mining, so one I'm writing here, Jaduguda. Apart from Jaduguda, nearby area, there's something called here, Turamdi. Then third place where we are carrying out mining, that is here, what is called as here, that is a place called Bandu Hurang. And all these are part of Singhbhum district only. Bandu Hurang, Turamdi, right? Then Jaduguda. Now this Bandu Hurang, what I've written here, this is something called open cast mine. What is the open cast mine? Now others are what? Underground mines. Underground. We go deep into the earth and then take out, just like coal or iron. But what is the open cast mine? Open cast mining is done into that kind of area, whether you talk about uranium or coal or iron ore or manganese, where it is not too deep into the earth, right? Shallow, near to the surface. It's like this one. Let's say, for example, you have this kind of uranium deposit here. Let's say uranium is found here. So what is done in the open cast mine, the surface is removed. Let's say, for example, one will unearth this kind of soil here. This will be removed. This soil is removed. Right, this part will be removed. Then again, this part of soil will be removed. It will go layer by layer. Layer by layer, until it comes to this part. It reaches to the part where the uranium is deposited. This kind of thing. It goes what? One by one. It's just like what I said, trenches. And then the uranium is taken out. Right? But this is more harmful. Why? Radiation, more exposure there. And on the other hand, what is the underground mines? Like this one. Tunnel through. We can tunnel through and can take it out. So in India, we too have open cast uranium mine, Bandu Hurang. There's a part of there. And at the same time, Tumlapalle we started. Now what happens there? What I've said in the classroom that when we take out the uranium, it is a mixture of 235 and 238. But for power generation, we require 235. So there's something called enrichment facility. So what comes the third stage is called enrichment. And there are technologies which are used for enrichment. See, remember that when you're talking uranium, it is not something heavier. It's very, very small. We cannot see with naked eyes. And one of the aspects, which I'll tell you that, one step which you will be aware, ultracentrifugation, where we can separate 235, 238. So generally, enrichment for worldwide, including power reaction, we require only 4 to 5%. What is required? 5% is the level of enrichment of what? Uranium-235. That is what is required. Where we require more enrichment? When we have to build nuclear weapons. Right? Let's say we want to make atom bomb. So there we get 25%, 30%. But for general power reaction, it has to be controlled one. So 5% enrichment is done. So we have a setup for that. But generally where we do enrichment, one is the place where we do the mining. So in Jaduguda, we have enrichment facility also. There is a facility has been made. Apart from Bark will also have. Right? Bark will also do the enrichment of uranium there. Then what comes here? After taking the uranium enrichment, next stage what is called here fabrication. There's a called as fabrication word comes here. Now what is fabrication? Let me write here. See, fabrication involves, I'll write all this one. The first thing is that we cannot take directly uranium and put into the reactor vessel. You have seen in the video also, still cylindrical tube is there. You have seen that where it is packaged with a pellet. You have seen that yellow color pellet. So what is done here? Solidified. Uranium is solidified into pellets. You have seen in the video there, this yellow color pellet that is there. Then what is done? These pellets are packaged into steel cylindrical tubes. The tubes are there where it is packaged there. Now it depends how much power we want to generate. 300 megawatt, 500 megawatt, 1000. There can be 50, there can be 100, or there can be 200. This kind of cylindrical tubes. This is called fuel rod. What is called as here is a fuel rods. So such fuel rods are made. They are referred to as fuel rods. And then what we do, we bundle it. We bundle this fuel rod to form fuel rod assembly. So what comes the last one here? Fuel rod assembly is prepared there. Right? Now I'm giving you the information. In India, fabrication technology has been worked out. There is a center for that, what is called Nuclear Fuel Complex in Hyderabad. In Hyderabad, we have a dedicated R&D center here, which is involved with the fabrication process. Right? After the fuel rods are made, the bundling is done, assembly is made, that is transported to each and every nuclear park. Let's say Kudankulam, Kalpakkam, right, Kakrapar, then Rawat Bhata, and then this fuel rod will go where? In the reactor. The reactor goes. So what comes the next one? The next what comes here? Power generation. The next stage comes here, power generation. Right? That goes into the power generation. So this will happen with the nuclear reactors built in the nuclear parks. There it is transported. Right? Now what will happen there? Once the power is generated, the rods, right, all will be used up. So what we have discussed in the classroom, that it will generate radioactive waste. Right? After the reaction is over. So we cannot simply take and put it outside. We have to take care of this highly toxic, hazardous radioactive waste. So now there comes a two process, what I'm writing here. The next stage, what is called as very important process called reprocessing. Right? So the next stage, what is required is reprocessing. Now what is the reprocessing? Remember that it is not that all the uranium will be used up. As you know that 238 we have been discussing that. So there will be leftover unused uranium. So what we do here is that, let me write here, recovery of, the first thing is that it helps the recovery of unused uranium so that we can use it again after fabrication. So unused uranium, right? And what will happen here in the process also? What I said in the classroom that it also results into plutonium. कुछ प्लूटोनियम भी बन जाएगा क्योंकि फास्ट न्यूट्रॉन होता है तो कुछ प्लूटोनियम है तो हम क्या करेंगे उस प्लूटोनियम को अलग कर देंगे और फिर उसको हम यूज करेंगे किसी और प्रोसेस में सो व्हाट कम्स हियर द सेग्रीगेशन सेग्रीगेशन ऑफ प्लूटोनियम and I have also mentioned earlier in the development part that today India is the leading producer of radioisotopes which you use in medicine. So in that process radioactive nuclei, daughter nuclei can also be radioisotopes be used in agriculture or medicine. इसमें कुछ ऐसे रेडियोआइसोटोप भी फॉर्म होंगे जो हम हेल्थ केयर में यूज कर सकते हैं तो उसको हम सेपरेट कर सकते हैं एंड दिस रेडियोआइसोटोप्स इट अगेन यूज technologies. It requires a sophisticated technologies. Right? Now remember that. If any country has acquired enrichment technology, this one, and reprocessing technology, that country can use both for civilian and military purpose. That means, remember that, if any country has completed this fuel cycle and has developed the respective technologies, enrichment, reprocessing, can develop nuclear weapon also. Because you can enrich, you can take what? Plutonium. And that can be used in weapons program. Right? Now after this one, reprocessing, whatever is left over will be highly toxic and hazardous. What we call nuclear waste management. We have to manage those nuclear waste. So what comes the next one? Next comes here, what we call nuclear waste management. This process is referred to as nuclear waste management. A small part of the nuclear waste management you have seen in the video. Small part of it, very, very brief. But there are a lot of things are there. What you have seen in the video? There was a box, right, and it was put into the well. You have seen, if you recall that video, where it is put into the, inside the earth, dumping into the earth, right? Such kind of a dumping is done. There's only one part of it. But actually, there are a lot of things are required for nuclear waste management, right? So what is done first is that all this nuclear waste from the fuel rods can be put into something called cement, just like houses we make the cement, concrete. Or we can heat at very high temperature. And we can use silicates. Also glass, glass matrix. We can embed that so that it can be stored somewhere. So what I'm writing here, nuclear waste management, let me write separately here so that you are able to, if in case you have to write in mains exam or something, or any competitive exam, such question comes, okay, how the nuclear waste management works there. The first is called, what I'm writing here, vitrification. The use of vitrification technology. There is a term called vitrification. Method to immobilize. I'm using the word here, immobilize radioactive waste into, here what I'm saying is glass matrix. What we do is that we heat at very high temperature and then we use silica. जैसे बैंगल वगैरह बनता है, ग्लास बनता है, तो what will happen, जब उसको कूल करेंगे तो ग्लास will be there. और उसके अंदर क्या होगा, it will be kept all the waste will be get immobilized. Then what we'll do that, we will store it for some time in some specially sealed unit, so the radiation should not go outside. So what is done here, for some time, second point is that storage there, storage in a, right, containment is there, total containment, it should not leak out to the environment. Sealed containment center or unit for, I'm now using the word here, sometimes depending upon the radioactivity, it can be 10 years or 15 years, but I'm writing here maximum 20 years. It's not that immediately dumped. We keep it for some time so that it goes lower and radiation level goes lower. And what comes the last? Let me write here on it so the people at the back can see. Now what is done here, let me just remove this part. The third part, what is done here is that dumped deep into the earth. Right, then what is done? Dumping is dumped into deep geological structure. Deep geological formations. So what type of formations will be preferred? When we say deep geological formations, so what all things will become there? Oceans could be one. Abandoned mines. I'll give you one good example. Kolar gold mines in Karnataka have been used for dumping purpose. So sometimes when we do the mining, when mining is over, so such places are now bare and abandoned. So there we can put into that and we can cover it. But what we have to take into account? Safety aspect. Why? There should not be any groundwater nearby. Some kind of water body should not be there. Right? Impenetrated rock should be there because it should not go into the environment. So there we put it to that. So there are sometimes guidelines also there. BARC maintains this kind of guidelines. Right? This is what called nuclear waste management. And vitrification technique मतलब है heating at very high temperature. And solidify करते हैं बहुत high temperature में 2000 degrees Celsius we heat that kind of waste there, right? So what have come here? Now what will happen there? Whatever we recover uranium, it can again go for enrichment and fabrication. We can repeat it. So for power generation using PHWR, we have to spend so much of money and develop such centers. Now this reprocessing and this nuclear waste management, the nuclear waste management, BARC comes. BARC is involved with nuclear waste management. Bhabha Atomic Research Center. It has come out with all guidelines to be followed in the country. Right? So whenever you come across this term nuclear fuel cycle, this cycle should come to your mind there. Okay, what exactly being referred to? Right? Another thing is that whenever you come across this word ENR technologies. So ENR technologies refer to two types of technologies, enrichment and reprocessing. Right? Two terms, enrichment systems and reprocessing systems are there. Okay? Now I've said what front end. So front end of the cycle is this one. I'm now putting into, let me use another color here. So front end, that which is done at the before power generation. Front end means before power generation. So what is before power generation? This part. This is called front end. Before we go for power generation, this is referred to as front end of the cycle. And what will be back end? After power generation. So that will be reprocessing and waste management. So this is referred to back end of the cycle. This is the back end cycle. But what I said here is that we are still using pressurized water reactor. And what type of pressurized water reactor we are using in the country? Heavy water reactor. So what we require for that? Manufacture of heavy water. So manufacture of heavy water will be auxiliary to the process there. Where we require heavy water? Power generation. For power generation in our reactor, we require deuterium oxide, heavy water. So here, production of heavy water. This heavy water in the PHWR, that is the auxiliary to the cycle. Auxiliary step is required. And there is a company, there is a board. We can say use not the company, we can use the word board, what is called Heavy Water Board in Mumbai. Heavy Water Board, Mumbai, is responsible for production of heavy water in the country. It is located in Mumbai. Up to fabrication. Right? Once we have made the fuel rod, after that go to power generation. That's good back end. After the power is generated, we go for back end. So I'll say this one. Survey exploration, mining, milling, enrichment, and fabrication are collectively called front end cycles, front end part of the cycle. And back end involves power generation, reprocessing, and nuclear waste management. This part comes into that. Right? And when you read India Yearbook, in the case of Atomic Energy Program, there are all this with the name of the centers and what then you know that India Yearbook सबसे problem क्या होता है? Too many facts. तो data देते इतना पैसे खर्च हुआ यहाँ किया वहाँ किया. So data and facts are not that important. What has been achievement in the last 1 or 2 years, that is given. But if you know something there, when you write main exam answer, let's say you get a question of achievement of DA in atomic energy in the country, or some kind of analytical question, so there you can mention that. This is what has been the past 2 years. Right? That part you can mention that part. Is it clear here, this one? Right? So from the concept point of view, so this is what you need to understand. Right? So now I'm coming to this part there. I'll open the India Yearbook and just briefly go to the pages there. And then I'll go to one report. As I said, we have been using nuclear technology to variety of areas. Other areas are there. I've already mentioned that in the science tech development. So I'll take you to a report of DAE. I've got a copy and same soft copy will be uploaded on your student portal, which will find agriculture, medicine, all those things in the area. Societal use, right? Societal aspect of that. If everybody has written, then I'll go into that part. Written there? Back at the back? Any question you have written right now? इसमें यही करना है कि just go back to the previous year question paper or any questions you have in a collection of that question bank. एक question bank है which you can which question bank you follow? Any unsolved question you practice for examination? Not yet. Okay. TMH has got 1,000+ questions. There is something called 1,000+ questions of TMH publication. Science and technology both. So what it is divided in 4 parts. Just simply go to our market. It's not a very thick one. With thin, a small one will be there. 1,000+ questions. A very useful one. What it has done for every subject: history, polity, geography, then science, technology. It gives you the first previous year questions. You have 15 years question, topic wise given. Every topic it is mentioned. Second, it is also gives you the questions for practice, where you can practice. At the back, it is given the hint and the answer. Right? So this gives you kind of whatever topic you study. Let's say today I've taught atomic energy. So when you take 1,000+ question, there is given atomic and nuclear technology. So you can solve 20-25 multiple choice question. So you'll get to know that how many questions you are doing it correctly. Right, about whatever we have learned there. Right, 1,000+. But I've said it comes for every other subject. Not only science, technology, for other subject also you have 1,000+ questions there. Right? Is it clear? So now let me open that report there. I'll remove this one. Done? All right. इसको ओपन करना है. Kolar mines in Karnataka. Karnataka has got Kolar gold mines. Is a abandoned mines. You'll find that. Now look at here. This is a soft copy of India Yearbook. So if you just Google, you'll find that. Right? You'll also find this particular India Yearbook soft is available online there. Chapter number 25. Just one second. क्या हुआ? ये चला गया? आ नहीं रहा? फिर से करना है? एक सेकंड. आ नहीं रहा. यहाँ तो है, वहाँ पर नहीं है. अच्छा टेढ़ी हो गई. अच्छा जस्ट वन सेकंड, वो वायरिंग का प्रॉब्लम है. हाँ नाउ सो okay, this is the part of the atomic energy. Right in the chapter number 25, India Yearbook, Science and Technology part, there you'll have this one. So what is given here is that Department of Atomic Energy established in 1954 is engaged in the development of nuclear power technology, applications of radiation technologies in the field of agriculture, medicine, industry and basic research. Some of these are increasing the share of nuclear power through deployment indigenous and other proven technologies, and also developing fast breeder reactors and thorium reactors with associated fuel cycle facilities. So now you understand what is fuel cycle facilities. So for thorium now we are working. For uranium we have already developed, now we are working for thorium or fast breeder reactor. Now what is given here? Building and operation of research reactors for production of radioisotopes and carrying out radiation technology, application in the field of medicine, agriculture industry. Then developing advanced technologies such as accelerators, lasers and encourage transport technology to industry. Support to basic research in nuclear energy related frontier areas of science. Right. Then contribution to national security. That comes weapons program, nuclear weapons and all this. Today our missiles are capable of carrying both conventional at the same time nuclear weapons, or what is said warheads, nuclear warheads, that comes there. Then you find here what? It says that what is saying this? The department comprises 5 research centers, 3 industrial organizations, 5 public sector undertakings and 3 service organizations. It has 2 boards, right? One is called Heavy Water Board. Second is called AERB, Atomic Energy Regulatory Board. So we have two boards also there. Now in mathematics and all is said here. Now after this, when you go to here, this part, stage 1. Nuclear power program, stage 1 or state 1, pressurized heavy water reactors and light water reactors. So whatever concept we have learned in today's class. But now it will give you what? Some kind of achievements. So what is said here, NPCIL has been given is a AAA credit rating by CRISIL and CARE. So it is a public sector company with a more quality, more in that kind of certification rating has been given. So for design, for construction, commissioning. Now in the video again, at the same time when you read newspaper, come criticality. What is meaning of criticality? When the reaction starts. How the reaction starts? A neutron, a beam of neutron is bombarded from outside. Once you have to start from outside source. But as you know that uranium itself will now keep on producing neutrons. So when we start and we control the reaction, we say that we have reached criticality. The process starts there. That is part comes. Then you will find all the data. All the data is given. So data is only just for at the background information. When you write main exam answer or essay type, there you can cite such data there. So given about Coulomb Coulomb, unit 2, 1000 megawatt, right? Then project under construction, Kakra Power Atomic Power Project, unit 3 and 4. So the reactors are decommissioned and in place of that, new reactors are constructed. So this is all data gives. Rajasthan Atomic Power Station 7 and 8. Now sanctioned projects. Right now you can see Gorakhpur Anu Vidyut Pariyojana, Haryana. I've said Haryana is very soon going to have nuclear park. This is what has been at advanced stage. You have the information. Then quality assurance. It gives you all the quality assurance and all these factors there. Now you come across this word WANO, W-A-N-O. Sometimes in PT exam, you come across question organization. I have mentioned one from IR is IAEA, International Atomic Energy Agency. So what type of body IAEA is there? Is intergovernmental, non-governmental? What type of body is that? Intergovernmental. India is also member of IAEA. Is it a UN body? United Nations body? Huh? Is it a UN body? Does it comes under UN organization? Like, you know, WHO, UNICEF, UNESCO, it doesn't come under that. It was originally started as an autonomous kind of organization. But I'll tell you that, though it was formed, but again, it is dealt under the UN there. But it has got independent status, right? What is the role of IAEA? What IAEA does? It is continuously coming newspaper. In what context? First, IAEA came in the recent times with Iran. Why? Now I understand. Iran was trying to make this. Iran was developing this fuel cycle. Because if Iran develop this fuel cycle, enrichment and reprocessing, so Iran can go for nuclear weapon also there. So that was geopolitical situation where Western countries tried to negotiate with Iran. So P5, Permanent 5 of Security Council, along with Germany, they brokered a deal with Iran not to go for the other kind of harmful like the weapon program there, only for the peaceful use. So that was the deal was signed with Iran. So at that time IAEA intervened to have for peaceful negotiation, not to have any kind of a deadlock between Iran and the Western countries. Right? That was the case there. IAEA also came in the news regarding Fukushima. Why? Nuclear safety, radiation. Because of that accident, the Daiichi nuclear plant. So IAEA also looks out into background radiation, the leakage radiation part. So IAEA is a main body which will come across in newspaper. What do you have here? WANO. Right? Here the word is World Nuclear Operator. Right? So WANO is not a intergovernmental. It is just a private, non-government organization. And it consists of members coming from operators. So what do you mean by operator? Those who operate the nuclear park or reactors. So in Indian context, which is the operator? NPCIL, not BARC. BARC is R&D unit there, is center there. Nuclear Power Corporation of India Limited, public sector company, operates reactor. Right? And in the operation of reactor, what is generated? Power. And that power is distributed through the grid. Right? Grid connected power. We are having today nuclear power as a grid connected power. It is distributed to several areas. So जो इंडिया का जो वानो का जो मेंबर है NPCIL है, ऑपरेटर बोलते हैं उसको, ठीक है. और एक और कंपनी मैंने क्लास में बताया था, भावनी. You have the name here. Bhartiya Navikiya Vidyut Nigam, another PSU. Right, they are called operators. Right, now you'll find here this information given that consultancy services. Now see here front end cycle. What I've said in the classroom. Front end cycle comprises operations such as mining, milling, processing of ore and fabrication of fuel. Right? Though here you don't have this cyclic given there. But when you read now, you'll be able to understand what it refers to. Right? This part is given there. Then what is given here? See here. In addition, production of heavy water. I made that auxiliary part to the cycle. Production of heavy water and this one, I use a moderator and coolant in pressurized heavy water reactor. Also considered a major program segment of the nuclear power program. Auxiliary to the cycle. Then what do you find here? DAE has wide-ranging capability in uranium mining and all this part. This is all information given. And you have the name here. Nuclear fuel complex at Hyderabad. Manufacture fuel assemblies for pressurized heavy water reactors, boiling water reactors and fast breeder reactors. There's 3 types of reactors mentioned. ठीक है, तो AHWR अभी केवल prototype है. But what we have come into this, these 3 types of reactors. You have information. Then you have heavy water board. Right, all the production heavy water board is, now what is saying here, see. Presently, I'll just highlight this part. Presently, heavy water board is not only self-sufficient in meeting the domestic demand of heavy water, but is also geared up to supply for future PSWRs and all this program there. So it has emerged as one of the important board located in Mumbai there, right? So large potential for non-nuclear application. Now see here, let me just come to this. Another very important point given. See what is given? Realizing the large potential for non-nuclear applications of deuterium and heavy water in life sciences, pharmaceuticals and technology areas. Heavy water board is also nurturing R&D activities in this area. Like the radio tracer used in nuclear medicine. So there the deuterium can be used. Right? Huh? As hydrogen का ही एक फॉर्म है ना, उसको आइसोटोप बोलते हैं, सेम एटॉमिक नंबर डिफरेंट मास नंबर. जो नॉर्मल जो वाटर उसमें भी ड्यूटेरियम होता है, बहुत ट्रेस में होता है, 0.01%, बट इट एग्जिस्ट देयर. राइट नाउ व्हाट इज वेरी इंपॉर्टेंट, सी हियर आई विल गिव यू वन नॉन न्यूक्लियर एप्लीकेशन. प्रिजर्वेशन ऑफ वैक्सीन, पोलियो वैक्सीन. पोलियो वैक्सीन प्रिजर्व यूजिंग ड्यूटेरियम ऑक्साइड. हेवी वाटर में इसको प्रिजर्व करते हैं, बिकॉज इफ यू कीप इट ओपन रूम टेम्परेचर द वैक्सीन समटाइम डिटोरिएट्स. So what I am giving you application, one medical application, preservation of vaccines using heavy water. Heavy water is used for preservation of vaccines. For example, polio vaccine. That is preserved using heavy water. There is a pharmaceutical use there, where we preserve that. Right? So you should not think only power generation. There can be other application of heavy water. Correct? So this is the information you have. Then preservation of vaccine, which I have said here. Now look at here. Fact. What is fact? Heavy water production, HWPs at Manuguru, then Kota, Hazira and Thai have carried out annual turnaround jobs during the period. So this is what you find is the name of the places in India where we are producing heavy waters. ठीक है, अब वो पता कर लें कौन सा स्टेट है. मनुगुरु कर्नाटका की लग रहा है ऐसे, such kind of names will be Karnataka name. Kota, you know that. Hazira, where is Hazira? Hazira is where? Gujarat is a very important pipeline is there. Hazira pipeline, refinery. That's Gujarat. Hazira is Gujarat. And Thai, ये Thai कहाँ से आ गया? Not Thailand there. Not Thai, it will be in India only. Right? So now you have facts and all this. Now diversification activities, all these things are given. So that part you now look at here, this one. Solvent technology. So therefore different type of solvents are there. Again now these will find that there's a name given there. But we'll come to important part. Now this boron enrichment. I've said that we are using boron as a control rod. The information given. So deployment of production of boron. So again heavy water board is involved with that. Then I've said also this sodium metal. Now see here, it's given here. Very clearly given. See, sodium is another important input for FBR, fast breeder reactor, used as coolant in the reactor. Right? So what is called learning in the classroom. If you learn that, if anytime question comes, they will not make mistake. Sodium is a coolant in FBR. Right? That part. Then you will find here, this one. Mineral exploration. I have said that Hyderabad, this one. Atomic Mineral Directorate. right? Now look at what is given here. This last sentence. Areas of Andhra Pradesh, Meghalaya, Rajasthan, Jharkhand. And I have given the names there. Domia Siat, Wakin, these all places we have the uranium deposit. And then uranium oxide, now it gives you the data here then. Then what do you find here? Geochemical survey, now look at here, which all places have been found out. There's some places also mentioned here. Haryana, Jharkhand, whatever it may be that. A drilling operation.
What is Sony drilling?
Sony drilling based on sound. Sound. We try to locate where the deposits are. Now what is given here? See here. Significant zones of total heavy mineral concentration have been located in Andhra Pradesh, Odisha and Tamil Nadu. Sonic drilling was initiated in beach sand investigations to evaluate deeper horizon. So what it is referring to? Monazite, thorium. So information from here tells you very clearly that it is not only Kerala, but there thorium can be found in other states also. But maximum abundance is where? Kerala. So कई बार यूपीएससी में क्वेश्चन आता है डायरेक्ट फैक्चुअल क्वेश्चन कि वेयर इन दैट रेयर मेटल्स आर एलिमेंट्स आर फाउंड और 4 जगहों का नाम दे दे और 4 स्टेट्स का नाम आ जाए. So many students will be thinking only Kerala, one only, but there may be 1 and 2 or 1, 2, 3 also be part of it. Yes, can be used for the nuclear weapons also.
It's being not allowed in NSC.
That's no, NSC has one more factor. This also there, because India has not signed NPT. Right. One of the criteria for nuclear suppliers group is that it is a signatory of NPT. India, Pakistan, Israel have not signed. There's weapons there. That's part of. But still, we are trying to gain access there. We are trying to getting access to the NSG. Why India is looking for NSG? It will open market for India. We can have more market there. Right. आज हमारे country में कुडनकुलम वगैरह रशिया आके build कर रहा है. There may be possible that one day we will building reactors in Sri Lanka and Bangladesh and Nepal and Bhutan. That can be there, right? This is what India is looking for. That is where energy comes here. Now look at here. UCI here, Uranium Corporation of India Limited. It is mentioned here. And what is given here? Now look at here. Jaduguda, Bhatin. Then Narwa Pahad, Turamdi, Bagjata. Bandhu Hurang, Moholdi, and all this. All these are places where uranium is mined. Oh no, these are Jharkhandi names, sir. They just, if some names comes from there, just these are place given, information. That's what I said. India yearbook has too many facts. The facts part can be supplemented by this kind of document there. And new mining and all this been found there. Now look at here, see. Tumlapalli, Andhra Pradesh, right? So, बस matter of time है. कब क्वेश्चन यूपीएससी एग्जाम में आता है. अगर आ जाता है तो उस समय मुझे याद कर लेना आप. This all question came with it. Right. So that is what I am trying to give you the extra information, so that in case the unknown areas where question can come, so you are prepared with that. So Tumlapalli is there, right? Now there's another company there. Now fuel fabrication. I mentioned nuclear fuel complex, Hyderabad, boiling water reactor. Then all facts will come there. Right. Back-end fuel cycle, fuel reprocessing and waste management. And there you'll find this word which I've used, vitrification. Now see here. This paragraph, see. Advanced, I'll highlight this. Vitrification system, Tarapur. And I've mentioned BARC, BARC, Bhava Atomic System. Completed vitrification of radioactive liquid waste in Joule melter. This part. See, UPSC will not ask what is vitrification, you explain. But when the keyword will come in the question, at least you know is linked with nuclear waste management. The name of the technology, where it comes into that. Right? So you'll find this kind of information given in the chapter there. Right? Now coming to societal use, that part which I'll upload in the soft copy there. Now societal use there, you'll come across this okay, chairman, let me come to that also there. There, I'll upload this document also, Chairman of Atomic Energy Commission. So all this, I have this. You can also download from DAE website, but is already with me. So I'll upload in on the student portal. So you have this all name, right from the very first chairman, Dr. Homi Jahangir Bhabha, Dr. Vikram Sarabhai. Then you have Dr. Homi N. Setna. Now he comes to a time frame when the India conducted first Pokhran. So if you can see the when he served as a chairman, 1972 to 83, and 74 we carried out Pokhran. So his role comes into the Pokhran test, Pokhran 1 test. Then comes here Raja Ramanna. I have said in the classroom, after DRDO he went to the atomic energy. So he served from 83 to 87. Then you have MR Srinivasan, right, from 87 to 90. And then comes another important scientist, is P.K. Iyengar, right, he's served as that. But Dr. Chidambaram, right, he is remembered for Pokhran 2. Dr. R. Chidambaram. Now how the second Pokhran differed from the first? Second Pokhran test and first one. That is difference. What is difference? No, both we carry out without Western countries knowing about it, that we are trying to have those kind of testing there. If US or any country came to know that India is going to have second Pokhran, then they would have thought it that. Both of these are underground tests only. Right? Why underground test? Not in water or air. India has signed, that's what said, when you read IR, there all this will come. India has signed something called Partial Test Ban Treaty, PTBT. What is Partial Test Ban Treaty? It allows only underground testing. आप water पे, surface पे, air पे कहीं नहीं कर सकते. Only underground testing is allowed. So since India is a signatory to PTBT, Partial Test Ban Treaty, which only allowed for underground test. So that's what we have gone into that. At the same time, what I said, not to be detected by satellite. We are planning something on the surface or something like that. Right? I'll add one more thing. There is again one treaty called CTBT, Comprehensive Test Ban Treaty, which bans all forms of test. But CTBT has not been signed and accepted by US, China and other countries. They are not signing, and India also maintains, if they will not do, we will not do that. Then let the developed countries come forward and sign the CTBT. So now there is a dispute. But what is CTBT? It allows all nuclear tests will be banned in future. If that treaty, CTBT, becomes a reality, it is going to have a very good impact worldwide in terms of the safety part of that, security part of it. So that is what you will also come across IR there. And all these are UN treaty, remember that. It comes under United Nations. India has PTBT, that's part. So what I said here, now tell me the difference again. Underground word is that is not the part. In 1998, Pokhran 2, India carried out thermonuclear weapon test. Hydrogen bomb was tested. There is one difference. In Pokhran 1, we only tested atom bomb. But second test, Pokhran 2, India carried out hydrogen bomb testing also. The hydrogen bomb is a thermonuclear weapon. That was also tested. Yield कम था, लेकिन किया. यानी कि इंडिया के पास हाइड्रोजन बॉम्ब भी बन सकता है और वो भी है, दोनों के लिए, दोनों की टेक्नोलॉजी है हमारे पास. So that was tested in Pokhran 2, 1998, during Atal Bihari Vajpayee as a Prime Minister. And that time, right, India declared that we will not carry any other further test. We gave that commitment. And that is being maintained by government. So only 2 tests, Pokhran 1 and 2. After that, no test. India, because we have acquired the technology, we don't need going for another test. Okay? So you have this name. Then Dr. Anil Kakodkar, right, chairman of, he was, now what is the role played by this person? Dr. Kakodkar. Dr. Anil Kakodkar played very important role in getting green access or access to NSG at the backdrop of Indo-US civil nuclear deal. Right, Indo-US civil nuclear deal. In that backdrop, India was able to get certain type of freedom, or you can say kind of waiver. The word is called waiver from NSG. Right? Why it was given to waiver to India, not to any other country? Because of India's stand, a peaceful stand that came into that. And you know the country like Canada, Australia, Japan, who were totally against India in giving the technology, now they have come forward and giving us enriched uranium. Like Canada has given us enriched uranium. Right? Australia have signed bilateral agreement. Japan has also now signed agreement with that. Right? Because of India's maintenance of that peaceful stand after 1974. So 40 years we have maintained that stand. So that waiver was given. At the same time, India is also trying to get access to NSG, to become a member of NSG. right? So Dr. Kakodkar's role is in getting that Indo-US civil nuclear deal signed and getting access to waiver from Nuclear Suppliers Group, NSG. Right, so eminent Indians you have this. Now here Sri Kumar Banerjee, who just in 2012 retired, and now presently is this Ratan Kumar Sinha. Right, he was earlier with NPCIL also there, and this is Sekhar Basu. He's from 2015 onward. Right, so all this is a chairman part of it. Then this societal use. ये है जो मैं आपको अपलोड करूंगा मैं कुछ चीज़ें मैं बता चुका हूँ और ये फोटोग्राफ जो आप देखेंगे तो विद प्राइम मिनिस्टर नरेंद्र मोदी विद ग्रुप ऑफ नर्सेस राइट ही इज हैविंग वन फोटोग्राफ हियर नाउ दिस फोटोग्राफ इज टेकन इन मंगोलिया एंड ड्यूरिंग दैट इवेंट व्हाट यू फाइंड visit to National Cancer Center of Mongolia while gifting of Bhavatron II. I've already covered in the classroom what is Bhavatron, right? Is a cancer treatment machine there. So at that time the photograph taken there. Right? A radiotherapy machine. So now we have given to Mongolia. And Bhavatron II is also given in India yearbook also. There again you will find that, right? Now same document, when you go to that, now I'll come to there's a address given to IAEA. Now look at it. What is the first thing given? Environment monitoring around nuclear reactors. Because you know, in and around nuclear reactors, there will be radiations. So there we are trying to do the monitoring part. So this is what is given there. Today, India is self-sufficient in building nuclear power stations and has gained mastery over the entire nuclear fuel cycle. And we are trying to do the monitoring so that if level goes higher, then any action can be taken there. Now for this, what you will find here, all this kind of testing is done. The samples are collected, they are looked into the gamma radiation, all this part. And what is the name of the board here? AERB, Atomic Energy Regulatory Board, that looks into. Now comes to the part which I have discussed in the classroom in the part of this one. Radiation technology developed in bark for value addition to food and agro commodities. I have said in the classroom food processing, right? So now you find here gamma rays. From where we get this gamma rays? Cobalt 60 and cesium 137. Right? Energy is also given. Energy part you don't have to memorize, but remember the accelerated electrons from accelerators. And then you have X-rays. Now look at here given. What are the technological benefits? Inhibition of sprouting in tubers, bulbs or rhizomes. There will not be sprouting part if we process using gamma rays. Right? This is given high dose. Then what is given? Insect disinfestation in stored grains, pulses and products. And what is third given here? Destruction of parasites in meat and meat products. And today we are carrying out, it is already being done in the market. Isko use mein laya gaya hai. Then what is you find? Medium dose. Elimination of spoilage of microbes in fresh fruits, meat and poultry. Then you have elimination of food pathogen in meat and poultry, hygienization of spices and herbs. Right? And third, high dose, sterilization of food for a special requirement. Right? And then you may ask me that, what about the safety if we eat those kind of food? Whether we will not get radiation, we will not develop cancer or tumor. So all these are done under international standard. So I'm coming to that standard also. Now see here is given. I'll read the sentence what is mentioned. In 1980, a joint FAO, Food and Agriculture Organization, IAEA, WHO Expert Committee on Food Irradiation, reviewed the extensive data on wholesomeness of irradiated foods collected up to that time. Now what comes here? 1983, very important name has been given. Codex Alimentarius is a commission which is formed by WHO, World Health Organization, and FAO, Food and Agriculture Organization. And today we are following Codex Alimentarius through FSSAI, Food Safety Standard Authority of India. And now you see here, ये सब allow किया गया इंडिया में. Let's say, for example, next year you get a PT question and they give you this one. Which of the food products, irradiated food products are allowed to be sold in the market? And you have the name given, 1, 2, 3, 4. Like the similar way of question was asked, where you find star rating on the appliances. Right? ceiling fan, then geyser, that was given. Right? AG mark was asked this year. AG mark and all this. So such question comes from such report. So what all things are given? Onion, potato, shallots, right? Then you have rice, semolina, suji and all this. Pulses, dried seafood, raisins, figs, dried dates, mango, आम का भी radiation होता है, right? Alfonso, right, which goes to outside India, that is radiated. Then you have what? Meat and meat products, frozen seafood and spices, garam masala, all this being done. And for what purpose? That is given on the third column. किस purpose के लिए किया जाता है? ठीक है? तो ये document, all this document which I will be providing on the student portal, you download it and keep it there, so that you can always use. At the same time, I'll also provide few more soft copy on the information part. Correct? Is it clear here? So I think now I have got class on 14th, I think. Yes. So 14th we'll discuss about defense technologies there. Is it clear? The concept part? And those who have got my book, Science Tech book, I have given in the part 2 and also part 3. All this you'll find collected in a very formatted form in part 3 of the book there. Right? And I have also given revision assignment, multiple choice question, which you can practice, right, for understanding more concept part of it. Right? Huh? नहीं वो नहीं है वो पब्लिशर के पास है ना कॉपीराइट देयर हाँ ई बुक नहीं है वो नाउ दे आर प्लानिंग देयर दे आर कमिंग दैट द मोमेंट आई गेट ई बुक आई विल शेयर विद यू दैट पार्ट राइट so till now it is a hard copy there. Okay, thank you everyone, we'll meet on 14th August, right? Thank you.